Your spacecraft is accelerating beyond Earth's orbit, carrying you outward from the blue planet that has been humanity's only home since life began there. You watch through the viewing port as Earth hangs against absolute blackness, oceans reflecting sunlight in brilliant blue patterns, while white clouds spiral across entire continents below. The atmosphere wraps the planet in a thin, glowing shell, visible now as a delicate edge where blue fades into black, thinner than the skin on an apple when compared to Earth's diameter. This is your starting point, the beginning of a journey that will carry you across 26,000 light-years of space to reach the bright center of the Milky Way galaxy. Earth fills the entire window before you, close enough that you can trace coastlines and watch weather patterns shift across its face in real-time observation. The Pacific Ocean spreads below, deep blue water interrupted by cloud formations that cast subtle shadows on the surface. Darkening patches of sea, while sunlight illuminates the surrounding areas in brilliant aquamarine. You can see the curve of the planet clearly from this distance, where the horizon bends into an arc instead of appearing flat as it does from the ground. Antarctica sits near the bottom edge of your view, its white ice cap bright against blue ocean, reflecting more sunlight than the darker land masses or water surfaces visible elsewhere. You are listening to the Drowsy Astronaut, and over the next few hours, we will travel together from Earth to the galactic center in one continuous journey across space. This is not a lecture about physics, but an experience, a slow voyage through real cosmic landscapes that you can picture and settle into as the evening deepens around you. But before we begin, feel free to share where you're listening from tonight in the comments below. And if this journey feels right for your late-night wandering mind, you might like the video or subscribe to join us on future voyages through the cosmos. Let us return our attention to the window, where Earth continues to shine in the sunlight, still close, still familiar, but already beginning to shrink as the spacecraft builds velocity. The moon appears off to the left, perhaps 50 times farther away than it appears from Earth's surface, its grey cratered face catching the same sunlight that illuminates the planet. You can see the dark Maria Plains and the brighter highland regions, the familiar pattern of light and shadow that creates the face cultures have seen in the moon since ancient humans first looked upward. No atmosphere surrounds the moon. No blue haze softens its edge the way Earth's atmosphere softens its boundary with space. So the transition from lunar surface to black space appears sharp and sudden. The moon travels in its orbit around Earth, the two bodies bound together gravitationally, a pair of worlds dancing through space, as they have for over 4 billion years. Space itself looks different from here than it appears from Earth's surface, where atmosphere scatters light and creates the blue daytime sky that hides the stars beyond. Here, beyond the atmosphere, darkness surrounds the spacecraft in every direction, except where Earth and Moon shine with reflected sunlight. And stars begin appearing as steady points, scattered across that darkness. They do not twinkle the way they seem to from the ground, where atmospheric turbulence causes their light to shimmer and shift, but hold perfectly still, constant in brightness and position. The sun itself remains out of your direct view in this particular window orientation, but you can see its light illuminating Earth and Moon, harsh and unfiltered, creating absolute shadows wherever surfaces block the direct rays. The spacecraft continues accelerating, using technologies that allow velocities far exceeding the speed of light. Though you feel no sensation of motion inside the protected cabin where gravity generators maintain comfortable conditions, Earth begins to shrink noticeably now, the details that were clear minutes ago becoming harder to distinguish as distance increases between you and the surface you departed from. Individual cloud formations blend together into white patterns. Coastlines lose their fine detail. The distinction between forest and grassland disappears as green and brown areas merge into broader color zones. You are leaving Earth at a pace that would have seemed impossible to earlier generations, yet the departure feels gentle and gradual. The home planet receding slowly across the hours, rather than vanishing in sudden acceleration. The Earth-Moon system becomes visible as a pair now, rather than two separate views requiring you to shift your attention from one window to another. Earth appears perhaps 4 times larger than the Moon from your current position, the size difference reflecting their actual diameter ratio. With Earth measuring roughly 12,700 kilometers across, while the Moon spans about 3,470 kilometers at its widest. The distance between them appears as empty black space, though you know that space contains traces of particles from both bodies. Atoms escaping from Earth's upper atmosphere, and dust particles knocked off the Moon's surface by meteorite impacts over billions of years. Together, they orbit their common center of mass, a point that actually lies inside Earth's volume, because Earth contains about 81 times more mass than the Moon, making Earth's gravitational influence dominant in their partnership. Colors remain vivid and clear through the window, unfiltered by any intervening atmosphere, showing you what these worlds actually look like under pure sunlight. Earth's blues range from the pale turquoise of shallow tropical waters to the deep navy of ocean basins kilometers deep, while its whites vary from the brilliant white of thick cloud tops to the slightly softer white of ice and snow covering polar regions and mountain peaks. The Moon's greys span from the almost black of some Maria floors where ancient lava flows created darker basaltic plains, to the bright grey of heavily cratered highlands where impacts have broken rock into fine powder that reflects more sunlight. Brown and green and tan colours mark Earth's continents, evidence of rock and soil and vegetation covering the land masses. But the Moon shows only variations of grey, no other colours existing on its airless, waterless, lifeless surface. The sense of departure settles over you now, not dramatic or emotional, but simply factual. The recognition that distance continues to increase and that the familiar details of home have already faded beyond clear viewing. You can no longer distinguish individual cities or mountain ranges, cannot pick out specific islands or lakes, cannot watch individual storm systems develop and move across regions. Earth has become a sphere of color hanging in darkness, beautiful and whole, all of its features blending into the general impression of a blue planet wrapped in white clouds with brown and green continents showing through gaps in the cloud cover. The Moon too has lost its surface detail, becoming simply a grey sphere marked by lighter and darker regions. The specific craters and mountain ranges no longer individually visible from this increasing distance. Starlight becomes more apparent around you as Earth's brightness diminishes with distance, the overall light level in the cabin dropping slightly as the main source of reflected sunlight grows smaller in the window. Stars that were present but unnoticed against Earth's glare now assert themselves as distinct points of light scattered in all directions across the sphere of space surrounding the spacecraft. Some appear brighter than others, not because they are actually more luminous, but because they lie closer to Earth in three-dimensional space. Their light taking fewer years to reach the position where you now travel. The brightest stars visible from Earth's northern hemisphere, stars like Sirius and Arcturus and Vega, appear somewhere in the vast scatter of points surrounding you. Though identifying specific stars becomes challenging when atmosphere no longer creates the familiar patterns of brightness and twinkling that ground-based observers use for recognition. The spacecraft's navigation systems continue guiding you along the planned trajectory, a path that will carry you first slightly inward toward the sun before curving outward and beginning the long journey across the galaxy's disk toward its center. You are traveling through the solar system's ecliptic plane initially, the flat, disc-shaped region where planets orbit, though your path will eventually take you out of this plane as you head toward the galactic center, which lies in a different direction than any planetary orbit extends. For now, Earth and Moon continue to dominate your attention. Two bright spheres against darkness, one blue and white and alive, the other grey and ancient and silent, both shrinking steadily as the distance between you and them expands at velocities that carry you millions of kilometers farther away with each passing hour. Earth's sphere has become small enough now that you can see it whole without moving your eyes, the entire planet visible in one glance, from pole to pole and across all longitudes that face toward your position. The Antarctic ice cap sits at one edge of the sphere, the Arctic regions at the opposite edge, though cloud cover obscures much of the northern polar area from your current viewing angle. The shadow line where day meets night on Earth's surface appears as a curve across the sphere, terminating Earth's illuminated side and marking the boundary where the sun has set for surface observers, where darkness has fallen, and where people perhaps look upward at stars that include the one you are traveling toward. You wonder briefly what Earth's sky looks like from the surface tonight, whether anyone looks up and thinks about the distances above them, the empty space reaching outward from the atmosphere through which you now travel. The Moon has separated visually from Earth in your window now, the two bodies appearing distinctly apart rather than close together. The 384,000 kilometers of average distance between them becoming apparent as they shrink with your departure. The Moon appears to trail behind Earth in their orbital dance, its slower position in orbit making it lag from this particular viewing angle. Though you know that both continue their gravitational partnership, regardless of how they appear from your changing perspective. Sunlight still illuminates both, though the intensity seems to diminish as your distance increases. Not because the light itself grows weaker, but because the bright disks of Earth and Moon occupy less of your visual field, allowing the surrounding darkness to dominate more of what you see through the window. Behind the Earth-Moon pair, the sun remains out of direct view, but its presence dominates this entire region of space. Its gravitational field controlling the orbits of everything within billions of kilometers. 8 planets orbit the Sun at various distances, along with hundreds of moons, thousands of asteroids, millions of comets, and countless smaller particles of rock and ice, all held in their paths by the star's immense mass pulling inward on everything nearby. You are leaving that system now, accelerating away from the Sun's innermost region where rocky planets circle close to the star's heat, heading outward on a trajectory that will eventually carry you beyond the Sun's gravitational control and into the darkness between stars. But that lies ahead, and for now Earth still holds your attention, growing smaller but remaining visible. A bright blue point that will soon fade among the countless other lights scattered across the infinite darkness surrounding your small moving window on the universe. Earth has become a bright star now rather than a sphere. Its details completely gone, its color reduced to a blue-white point that shines steadily among the other stars scattered across space. The moon has vanished as a separate object, its light too dim to remain visible at this distance, merged with Earth's brightness, or lost entirely against the background scatter of more distant starlight. You are perhaps several million kilometers from Earth now, the distance continuing to grow, the home planet receding into the general star field that surrounds you in all directions. Soon, it will fade beyond even this level of visibility, and then Earth will be gone from view entirely, hidden among thousands of other points of light, indistinguishable and lost. But ahead, the inner solar system waits, and the Sun's realm opens before your journey, a region of intense light and rocky worlds where temperatures soar and surfaces bake under unfiltered stellar radiation. The next region through which our path must travel. The Sun dominates the view ahead now, though filters on the spacecraft's windows reduce its overwhelming brightness to levels safe for direct viewing. You can see the star's surface from this distance, a roiling sphere of plasma heated to temperatures of about 5,500 degrees Celsius. At the visible layer, though far hotter in the core where fusion processes generate the energy that makes the Sun shine. The surface appears textured rather than smooth, covered in a pattern of bright cells called granules, each one roughly the size of a large Earth nation, where hot plasma rises from below, cools slightly, and sinks back down in continuous circulation. Darker spots interrupt the bright surface in several places. Cooler regions, where magnetic fields suppress the normal convection, appearing dark only by contrast, though these sunspots still glow at temperatures that would vaporize any known material instantly. The Sun's light fills this inner region of the solar system, illuminating everything within hundreds of millions of kilometers, creating the bright environment where Mercury and Venus orbit, close to the star's heat. You are traveling through this zone now, not stopping at the Sun itself, but passing through the inner system on your trajectory that will eventually curve outward and carry you toward the galaxy beyond. Space here feels different than it did near Earth, warmer in the sense that radiation levels are higher, brighter because the Sun's proximity makes its light more intense, though the spacecraft's environmental systems maintain comfortable conditions inside regardless of external radiation. The emptiness remains absolute, vacuum extending in all directions, but the Sun's presence makes this emptiness feel less dark, less cold, less isolated than the deeper space that lies ahead. Venus appears off to your left, brilliant white against the blackness, reflecting more sunlight than any other planet in the solar system, due to its thick cloud cover that bounces about 75% of incoming light back into space. The planet shows as a smooth, featureless sphere from this distance, its entire surface hidden beneath clouds of sulfuric acid droplets that extend from about 40 to 70 kilometers above the ground, completely obscuring any view of the rocky surface below. The clouds themselves appear yellowish white, their color created by sulfur compounds mixed with carbon dioxide, forming a thick atmospheric blanket that traps heat through an extreme greenhouse effect and raises surface temperatures to about 470 degrees Celsius. You watch Venus for a time as the spacecraft continues its trajectory, seeing how the planet's brightness remains constant, how no surface features show through the perpetual cloud layer, how it hangs alone in its orbit, like a bright lamp suspended in darkness. The sun's corona becomes visible at the star's edges, where the filters allow you to see the faint outer atmosphere extending beyond the bright surface. Streamers of plasma stretch outward from the sun's equatorial regions, following magnetic field lines that guide charged particles away from the star and into space, creating structures that reach millions of kilometers beyond the visible surface. The corona's temperature exceeds 1 million degrees Celsius, despite being further from the sun's core than the cooler surface below, a phenomenon that puzzled scientists for decades until they understood that magnetic waves carry energy outward and heat the tenuous outer atmosphere to these extreme temperatures. During solar maximum periods, when the sun's magnetic activity peaks, every 11 years or so, the corona appears more symmetrical and bright. While during solar minimum, it shows more structure and extends farther at the equator than at the poles. Mercury comes into view as the spacecraft's trajectory carries you past the sun's position and allows you to see inward toward the star's closest planetary companion. The small world orbits at an average distance of about 58 million kilometers from the sun, though its elliptical orbit carries it as close as 46 million kilometers at perihelion and as far as 70 million kilometers at aphelion, a variation much larger than Earth experiences in its more circular orbit. Mercury itself appears grey and heavily cratered, resembling Earth's moon in many ways, its surface ancient and airless, and marked by billions of years of meteorite impacts that have left scars ranging from tiny pits to enormous basins hundreds of kilometers across. The planet rotates slowly relative to its orbit, taking 58 Earth days to complete one rotation, while orbiting the Sun every 88 Earth days, creating a resonance where Mercury rotates exactly 3 times for every 2 orbits it completes around the star. The character of space in this inner region differs from the space near Earth in subtle ways that become apparent as you observe your surroundings more carefully. Dust particles appear more frequently here, small fragments of rock and metal and ice scattered through the inner solar system, remnants from the formation period when rocky planets coalesced from a disk of material orbiting the young sun. The zodiacal light phenomenon visible from Earth originates from sunlight reflecting off this dust, creating a faint glow along the ecliptic plane that observers sometimes see before dawn or after sunset. Evidence of the thin haze of particles that fills the space between planets. The solar wind streams past the spacecraft continuously, though you cannot see it directly. A flow of charged particles expelled from the sun's outer atmosphere at speeds of several hundred kilometers per second, carrying magnetic fields outward and creating a dynamic environment throughout the region. Sunlight itself appears different here than it does when filtered through Earth's atmosphere and diffused across a sky, arriving as parallel rays from a point source, creating harsh shadows and bright highlights without any of the softening effects that atmospheric scattering provides. Surfaces in direct sunlight glow brilliantly, heated to temperatures that would destroy unprotected materials, while surfaces in shadow drop to temperatures hundreds of degrees colder within centimeters of the illuminated areas. No atmosphere existing to transfer heat from hot regions to cold. The contrast between light and shadow appears absolute. No gradual transition from bright to dark, but an immediate boundary where sunlight either reaches or does not reach, where protection exists or does not exist, where heat radiates in or radiates away, with nothing to moderate the extremes. Venus continues to shine in the distance, as your trajectory carries you past its orbital distance and curves gradually outward from the sun's proximity. The planet moves in its orbit at about 35 kilometers per second, fast enough to circle the sun in just 225 Earth days. Though its own rotation takes 243 Earth days to complete, making its day actually longer than its year, in a peculiar arrangement unique among the major planets. Venus rotates backward compared to most other planets, spinning east to west rather than west to east, likely the result of a massive impact early in its history that tipped the planet over and reversed its original rotation direction. Despite its brightness and proximity to Earth, Venus remains hostile to human presence. Its surface pressure, 92 times Earth's atmospheric pressure at sea level, enough to crush unprotected spacecraft. While its temperature exceeds the melting point of lead, and its atmosphere contains clouds of corrosive sulfuric acid. The sun appears smaller behind you now as the spacecraft accelerates outward from the inner system, though it remains far larger and brighter than it appears from Earth's distance, still dominating the sky with its presence. The star's light output remains constant to within a fraction of a percent over short timescales. Though sunspot cycles cause slight variations in total energy emission, and the sun gradually brightens over millions of years as fusion processes change the core's composition. Every second, the sun converts about 600 million tons of hydrogen into helium through fusion reactions, losing about 4 million tons of mass in the process as energy radiates away, according to Einstein's equation, relating mass to energy. This process has continued for about 4.6 billion years and will continue for roughly another 5 billion years before the sun exhausts its core hydrogen and begins evolving into a red giant star. Mars appears ahead now, its reddish color distinctive even from millions of kilometers away. The tint created by iron oxide minerals that cover much of the planet's surface and give the world its characteristic rust-colored appearance. The planet orbits at a distance of about 228 million kilometers from the Sun on average, placing it just beyond Earth's orbit in the solar system's architecture. Though its more elliptical orbit means the Earth-Mars distance varies considerably depending on where both planets are in their respective orbital cycles. From your current position, Mars shows a visible disk rather than just a point of light, and you can make out darker regions and brighter regions across its surface. Variations in color and reflectivity that early telescopic observers mapped and named, thinking perhaps they saw continents and seas, though we now know the darker regions are simply areas where less dust covers the underlying volcanic rock. The spacecraft continues its outward trajectory, leaving the inner solar system behind, moving away from the sun's intense radiation and the rocky worlds that orbit close to the star's warmth. The brightness surrounding you diminishes gradually as the sun's light spreads across ever larger spheres of space, its intensity falling according to the inverse square law that governs how radiation disperses with distance. What was blindingly bright near Mercury becomes merely bright near Earth's orbit, and will become dimmer still as you travel outward past Mars, toward the asteroid belt and the realm beyond where giant planets orbit in cold and distance. The inner system has shown you the sun's power and proximity, the rocky worlds baked by stellar radiation, the harsh environment where temperatures soar and atmospheres either vanish or thicken into crushing greenhouse prisons. Ahead lies a different environment, a transition zone where rocky gives way to ice, where small worlds give way to giants, where the sun's warmth fades and the outer solar system begins. Temperature continues dropping as distance from the sun increases. Not that you feel it inside the climate-controlled spacecraft, but the external environment grows colder as radiation from the sun spreads thinner across the growing sphere of space surrounding the star. Objects at Earth's distance receive about 1,360 watts of solar energy per square meter facing the sun, enough to warm surfaces and drive weather and sustain liquid water in the right atmospheric conditions. Mars receives only about 590 watts per square meter due to its greater distance, giving the planet a colder average temperature around -60 degrees Celsius, despite its thin atmosphere providing minimal greenhouse warming. The asteroids ahead receive even less, and the giant planets beyond them receive far less still. Cold increasing with distance in a mathematical relationship that shapes the character of each planetary environment and determines what materials can exist in solid, liquid, or gaseous form at each location. The transition from inner to outer solar system holds a boundary quality, though no actual barrier exists in space to mark where one region ends and another begins. The inner system consists primarily of rocky material because temperatures near the young sun were too high for volatile compounds like water, methane, and ammonia to condense into solid form. So only metals and silicate minerals remained to build the terrestrial planets. Beyond what scientists call the frost line, which lay somewhere around the current orbit of Mars in the early solar system, temperatures dropped low enough for water ice and other frozen volatiles to remain solid, providing much more material for planet building and allowing the giant planets to grow massive enough to capture hydrogen and helium from the surrounding nebula. You are crossing through this transition zone now, leaving the warm rocky domain behind, entering the cold realm ahead where ice becomes common and where the giant planets grew to sizes that dwarf the Earth many times over in both mass and volume. Venus has faded to a bright point behind you. Mercury, lost entirely against the sun's glare, and Earth, invisible among the scatter of background stars at this distance and angle. The Sun itself remains the dominant light source, but its disk has shrunk noticeably from the enormous sphere it appeared when you first departed Earth's orbit, becoming smaller and more distant as your journey carries you outward at velocities that cover astronomical distances in compressed time. Ahead, the asteroid belt waits, and beyond it, Jupiter's massive presence begins to influence the orbital architecture of the outer solar system, its gravity shaping the distribution of smaller bodies and clearing gaps in the asteroid population through resonance effects that have persisted for billions of years. The inner solar system fades behind you now, and the transition zone ahead beckons, a region of scattered rocky bodies tumbling through space between the terrestrial planets and the distant giants. The next stage of this journey outward from Earth and toward the galaxy beyond. The asteroid belt region opens around you as the spacecraft travels outward beyond Mars. Though the term belt suggests a crowded field of rocks, when the reality shows mostly empty space, with occasional small bodies scattered across enormous volumes. The asteroids themselves orbit the Sun between roughly 330 million kilometers and 480 million kilometers from the star, occupying a zone where a planet might have formed if Jupiter's gravity had not disrupted the accumulation process billions of years ago. You peer through the window, watching for these small worlds, knowing that millions of asteroids, larger than 1 kilometer, exist in this region. Yet space remains so vast that collisions between them happen only once every few tens of thousands of years on average. The darkness continues around you, punctuated now not just by distant stars, but by closer objects moving through space in their ancient orbits. Worlds too small to become spherical, too irregularly shaped to be called planets, but substantial enough to have survived since the solar system's formation. An asteroid appears ahead, growing slowly larger as your trajectory carries you past its orbital path. A small world, perhaps 30 kilometers at its longest dimension, tumbling end over end in a slow rotation that takes several hours to complete. Its surface appears grey-brown and heavily cratered, pockmarked by impacts from smaller bodies that have struck it over billions of years. Each collision chipping away fragments and creating the rough landscape of overlapping craters that covers the entire visible surface. No atmosphere surrounds this small body, its gravity far too weak to hold any gases against the evaporation pressure from molecular speeds and solar radiation. So its surface lies exposed directly to space and has remained essentially unchanged except for impacts since the asteroid's formation. You watch it tumble, noting how one side appears slightly darker than the other, perhaps indicating a different mineral composition in that region, or maybe just a variation in how much fine dust covers the underlying rock in different areas. The asteroid drifts past your window as the spacecraft continues outward, and you notice how silence and stillness characterize this environment, despite the motion all around you. The asteroid tumbles silently, no air existing to carry sound, even if some process created vibrations. The vacuum, absolute and complete in every direction. Smaller rocks drift in space nearby, fragments perhaps knocked off the larger body by ancient impacts, each piece following its own orbit around the Sun, each traveling at roughly the same speed as its parent body, but gradually separating over millions of years as tiny velocity differences accumulate into larger distances. The Sun illuminates one side of each object sharply, leaving the opposite side in complete darkness. The harsh lighting creating dramatic contrasts between bright and dark that no atmospheric scattering exists to soften or moderate. More asteroids appear as you travel deeper into the belt, though they remain separated by distances of hundreds of thousands or even millions of kilometers, never crowding together the way illustrations sometimes suggest. You see perhaps a dozen asteroids visible at once, in different parts of the sky, ranging from small irregular bodies just a few kilometers across to larger ones that span 50 or more kilometers in their longest dimension. Each tumbles in its own pattern, rotation rates varying from a few hours to several days, depending on the body's size and mass distribution and the history of impacts it has experienced. Some appear roughly spherical despite their small size. Their shapes smoothed by perhaps once having enough internal heat to partially melt and reshape their interiors before cooling and solidifying into their current forms. Others look like collections of rubble, barely held together by weak gravity, their surfaces showing scattered boulders and deep shadows where large rocks create gaps and irregularities across the landscape. The larger asteroids in the belt have names and known characteristics from decades of telescopic observation and more recent spacecraft visits. Ceres, the largest by far, measures about 940 kilometers in diameter and contains roughly 1/3 of the total mass in the entire asteroid belt. Massive enough that its gravity pulled it into a spherical shape that qualifies it as a dwarf planet by modern classification. Vesta comes second in mass, though not in size, about 525 kilometers across, with a surface that shows evidence of ancient volcanic activity and a massive impact crater near its south pole that excavated material down to the interior mantle. Pallas and Hygiea rank as the next largest bodies, each several hundred kilometers across, each containing enough mass to represent significant accumulations of the material that failed to form a planet in this region when Jupiter's gravity stirred the orbital velocities too high for gentle collisions and mergers to occur. The asteroids show surprising variety in composition and appearance, despite all being remnants from the same formation era billions of years ago. Some appear very dark, reflecting only a few % of the sunlight that hits them, their surfaces covered in carbon-rich minerals that give them nearly black appearances, similar to charcoal. Others shine brighter, reflecting 20 or 30% of sunlight, their surfaces composed of lighter-colored silicate rocks or even exposed metal where impacts have broken through to iron-nickel cores. The reddish color that characterizes some asteroids comes from iron oxidation over billions of years of space weathering, while others remain gray or even slightly bluish, depending on their mineral composition. These differences tell scientists about where in the early solar system each asteroid formed, with different temperature zones producing different available materials that condensed and stuck together during planet formation. Jupiter begins to appear ahead now, still millions of kilometers distant, but visible as a bright point that will gradually grow into a disk as you approach the outer solar system's first giant planet. The giant's presence has shaped the asteroid belt throughout solar system history, its massive gravity creating resonance regions where asteroids cannot maintain stable orbits over billions of years. Gaps appear in the asteroid distribution at certain distances from the Sun, where orbital periods create simple ratios with Jupiter's own period. Locations where gravitational perturbations gradually eject asteroids into different orbits and leave empty zones called Kirkwood gaps after their discoverer. The belt itself exists because Jupiter prevented a planet from forming here, the giant's gravity stirring the orbital velocities of rocky planetesimals too vigorously for them to collide gently and merge, instead causing high-speed impacts that fragmented bodies rather than allowing them to grow larger through accumulation. You pass several more asteroids as the spacecraft continues outward, each one a small world with its own shape and history, each tumbling through space on an orbit that has remained essentially the same for billions of years. Some asteroids show evidence of having been parts of larger bodies that broke apart in catastrophic collisions, their shapes angular and irregular as if cleaved from bigger parent bodies. Their surfaces showing fresh-looking fractures that expose brighter material beneath the darker space-weathered outer layers. Other asteroids appear to be loose collections of rubble from multiple parent bodies, gravitationally bound but not solid, their structures like bags of rocks, barely holding together, vulnerable to disruption if they spin too fast or experience too strong a gravitational encounter with a passing planet or another asteroid. The spacing between asteroids reinforces how empty space truly is, even in regions we call belts or fields or clouds. You might travel for hours through the asteroid belt, seeing nothing closer than the distant stars, then encounter one small body, then continue for hours more before another appears. Science fiction depictions showing dense fields requiring navigation skill to avoid constant collisions have no basis in reality. Where spacecraft routinely pass through the asteroid belt without seeing any asteroids close enough to appear as more than distant points of light. The total mass of all asteroids combined amounts to only about 4% of the Moon's mass. All that material scattered across a volume so enormous that density drops to nearly zero when averaged over the belt's total volume. Space wins in the competition. Between matter and emptiness, the distances between objects always greater than the objects themselves, the void always more prevalent than the substance. The sun continues to shrink behind you as the journey carries you further from the star's position. Its disk, now perhaps 1/3 the size it appears from Earth, and much smaller than it looked from Mercury's vicinity, where you began this outward passage. Light from the sun still dominates illumination in this region, still provides enough energy that solar panels could power equipment if needed, though the intensity has dropped to perhaps 1/20th what Mercury experiences in its scorched proximity to the star. Temperature in sunlight here hovers around -73 degrees Celsius. On average, for a body with no atmosphere, cold enough to freeze carbon dioxide, but not cold enough for methane or nitrogen to remain solid. Water ice becomes stable at the surface in permanently shadowed crater regions where sunlight never reaches. And some asteroids do show spectroscopic evidence of surface ice in protected areas where evaporation rates remain low enough for ice to persist over geological time. Jupiter's brightness increases steadily ahead, the planet growing from a point to a visible disk as distance decreases, though you remain millions of kilometers away still and cannot yet distinguish individual features on its cloud-covered surface. 4 tiny points of light arrange themselves around Jupiter's disk in a pattern that changes slowly as you approach. The 4 largest moons discovered by Galileo when he first turned a telescope toward the planet in 1610. Io, Europa, Ganymede, and Callisto orbit Jupiter in a miniature solar system, each moon large enough to be visible from Earth with small telescopes, each world different in composition and character from its siblings, despite sharing the same giant planet as their gravitational anchor. You watch these points of light surrounding Jupiter, seeing how they maintain their positions relative to the planet, how the system appears as a single organized structure rather than random objects scattered through space. The asteroid belt represents the transition zone between inner and outer solar system, the boundary region where rocky terrestrial planets give way to giant worlds dominated by gases and ices. Behind you lie Mercury, Venus, Earth, and Mars, each one a rocky sphere with a metal core, each built primarily from materials that could condense in the hot inner regions of the young solar nebula. Ahead lie Jupiter, Saturn, Uranus, and Neptune, massive worlds composed mostly of hydrogen and helium, with smaller cores of rock and ice, planets that grew large enough to capture the light gases that make up most of the Sun's mass and most of the galaxy's normal matter. The asteroids themselves represent the leftover building blocks, the material that never assembled into a planet, frozen in their orbits like archaeological remains from the solar system's formation era. You are crossing through this museum of ancient fragments, these small worlds that preserve evidence of conditions 4.5 billion years ago, when everything now existing began its long history of orbits and evolution and change. The outer edge of the asteroid belt passes beneath you as the spacecraft's trajectory carries you beyond the main concentration of rocky bodies and into the gap between the belt and Jupiter's orbit. Asteroids become less frequent, the gaps between sightings growing from hours to days in normal travel time, though your faster-than-light journey compresses the experience into manageable duration. Space returns to its typical character, empty and dark and vast, punctuated only by distant starlight and the growing brightness of Jupiter ahead. The giant planet dominates the view now, no longer just a bright point, but a visible disk, showing faint banding even from this distance. A world so large that 11 Earths could fit across its diameter, and 1,300 Earths could fit inside its volume. The outer solar system opens before you, the realm of cold and distance, of giant planets and dozens of moons, of faint sunlight and temperatures that drop low enough for exotic ices to form and persist. The next region through which this journey must travel on its path from Earth to the galactic center. Jupiter fills more of the window as you approach, its enormous size becoming apparent even from millions of kilometers away, the planet's disk showing clear color banding in parallel stripes across its face. The clouds appear in alternating zones of cream white and orange brown, with subtle variations of tan and yellow and reddish tints, marking different belt and zone regions where atmospheric chemistry and temperature create different hazes and particles. These bands run parallel to Jupiter's equator, driven by the planet's rapid rotation that spins the entire massive world around in just under 10 hours, creating powerful east-west wind systems that organize the clouds into the stable pattern visible from great distances. The Great Red Spot appears as an oval reddish region in the southern hemisphere, a storm system larger than Earth that has persisted for at least 350 years of continuous observation, and perhaps much longer. Rotating counterclockwise in a high-pressure anticyclone, that towers above the surrounding cloud deck. The 4 Galilean moons become individually distinguishable as you draw closer, each one showing as a small disk rather than just a point, each world different from its siblings, despite orbiting the same parent planet. Io appears yellowish-orange, its surface covered in sulfur compounds deposited by volcanic eruptions that make it the most geologically active body in the solar system, with hundreds of active volcanoes continuously resurfacing the moon and ejecting material into space. Europa shows a pale cream color, its surface composed of water ice that covers a global ocean perhaps 100 kilometers deep. Beneath the frozen crust, the ice marked by long linear fractures and relatively few impact craters, indicating ongoing geological activity that erases older surface features. Ganymede appears grey and heavily cratered in some regions, with lighter grooved terrain in others. The largest moon in the solar system, exceeding even Mercury in diameter, though containing less mass due to its mixture of rock and ice, rather than Mercury's iron core and rocky mantle. Callisto appears uniformly dark grey and heavily cratered across its entire visible surface, showing less geological activity than the other 3 large moons. Its ancient face preserving impact scars from billions of years of bombardment. Jupiter's size becomes overwhelming as you pass through its orbital region. The planet spanning about 143,000 kilometers at its equator and containing more mass than all other planets in the solar system combined, though still only about 1,000th the Sun's mass. The giant planet rotates so fast that its equatorial regions bulge outward noticeably, while its poles flatten inward, creating an oblate spheroid shape rather than a perfect sphere, with the equatorial diameter exceeding the polar diameter by about 9,300 kilometers. Clouds visible at the surface represent only the upper layers of an atmosphere that extends thousands of kilometers downward, transitioning gradually from gas to liquid without any solid surface existing anywhere in the planet's structure, except perhaps a rocky core deep in the interior where pressures exceed millions of Earth. Atmospheres and temperatures reach tens of thousands of degrees. The spacecraft's trajectory carries you past Jupiter at a safe distance. The planet's powerful magnetosphere generating radiation belts that would damage unshielded equipment and pose serious hazards to any biological organisms exposed to the high-energy particles trapped in the magnetic field. Jupiter's magnetic field exceeds Earth's by about 20,000 times in strength at the cloud tops and extends millions of kilometers into space, creating a magnetosphere so large that if it were visible from Earth, it would appear several times the size of the full moon, despite Jupiter's enormous distance. The moons orbit within this magnetic environment, with Io particularly affected as the moon's volcanoes eject ions that become trapped in the field and create a torus of plasma around Jupiter's orbit, glowing in ultraviolet light and creating intense radiation near Io's orbital distance. Saturn becomes visible ahead as Jupiter recedes behind you, the ringed planet appearing first as a bright point that gradually resolves into a disk with a thin line extending outward on both sides as the famous ring system comes into view. Even from millions of kilometers away, the rings stand out as the dominant feature, making Saturn instantly recognizable and visually distinct from every other planet in the solar system, despite similar giant size and gaseous composition to Jupiter. The planet itself appears pale yellow gold in color, its clouds less vividly banded than Jupiter's, but still showing parallel stripes and occasional storm systems in the atmosphere, the muted colors resulting from a high-altitude haze layer that obscures the deeper cloud features that show more clearly on Jupiter. The character of space continues to change as you travel outward from the Sun, the star now appearing much smaller and dimmer than it did near Earth. Its disk shrunk to perhaps 1/9 the angular size visible from home, and its light intensity dropped to about 1% of what Earth receives. Temperature for an airless body this far from the Sun would average around -180 degrees Celsius in sunlight, cold enough that water ice behaves like rock and remains solid indefinitely, while methane and ammonia begin to freeze at the surface in permanently shadowed regions. The outer solar system has transitioned from rocky to icy, from warm to cold, from bright to dim, though the Sun still provides far more light here than any other star could offer, still dominates illumination and heating, still determines the orbital structure through its gravitational field. Saturn's rings resolve into greater detail as you approach, showing not a single smooth disk, but a complex system of thousands of individual ringlets, separated by gaps and divisions where gravitational resonances, with Saturn's moons, clear particles from certain orbital distances. The rings extend from about 66,000 kilometers to about 480,000 kilometers from Saturn's center. Though most of the visible mass concentrates in the main A, B, and C rings that span from 74,000 to 140,000 kilometers from the planet's center. The ring particles themselves range in size from tiny grains smaller than sand to chunks larger than houses, all composed primarily of water ice with some rocky material mixed in, each particle following its own independent orbit around Saturn, that collectively creating the appearance of a solid disk when viewed from a distance. The rings show subtle color variations as you observe them from different angles, with the B ring appearing brightest white and the C ring appearing more translucent and grey, while the A ring shows intermediate brightness with a noticeable gap called the Encke division, where a small moon called Pan orbits and clears a path through the ring material. The rings appear incredibly thin relative to their diameter, extending hundreds of thousands of kilometers across, but measuring only about 10 to 100 meters thick in most regions, making them proportionally thinner than a sheet of paper would be relative to a typical room. Sunlight passes through the thinner C ring somewhat, allowing you to see Saturn's globe behind it, while the denser A and B rings appear opaque and cast shadows on the planet's cloud tops below, where they block the Sun's rays. Saturn's moons number over 80 confirmed satellites, ranging from tiny irregular bodies probably captured from passing asteroid or comet populations to massive Titan, the second largest moon in the solar system, and the only moon with a substantial atmosphere. Titan appears as a hazy orange disk in the distance, its thick nitrogen atmosphere obscuring the surface completely beneath organic haze layers that give the moon its distinctive color. The atmosphere's pressure at Titan's surface exceeds Earth's sea level pressure by about 50%, making Titan the only moon where a human could walk on the surface in just a heated suit, rather than requiring a full pressure suit. Though the temperature of -179 degrees Celsius would still require serious thermal protection. Lakes and seas of liquid methane and ethane cover parts of Titan's polar regions, the only surface liquids existing anywhere in the solar system besides Earth's water oceans. Though these lakes remain at temperatures that would instantly freeze water into ice, harder than steel, the spacecraft continues its outward journey, leaving Saturn behind as the trajectory carries you toward the outer reaches of the planetary solar system, where Uranus and Neptune orbit in cold isolation. The distance between planets increases dramatically in the outer system, with Saturn orbiting at about 1.4 billion kilometers from the Sun, and Uranus at about 2.9 billion kilometers, nearly twice Saturn's distance and more than 20 times farther from the Sun than Earth orbits. The gap between these giants stretches across more than 1 billion kilometers of mostly empty space, a vast region containing only scattered small bodies and the thin solar wind pushing outward from the Sun against the slowly increasing pressure of the interstellar medium beyond. Uranus appears ahead eventually, a pale blue-green disk tilted dramatically so that its north pole points almost directly toward the Sun during one part of its 84-year orbit, making it appear to roll along its orbital path rather than spinning upright. Like most planets, the unusual tilt, about 98 degrees from the perpendicular to its orbital plane, probably resulted from a massive collision early in Uranus's formation that knocked the planet onto its side, creating the extreme seasonal variations where each pole experiences 42 years of continuous sunlight, followed by 42 years of continuous darkness. The planet's blue-green color comes from methane in its atmosphere, absorbing red light and reflecting blue and green wavelengths back into space, giving Uranus its distinctive appearance that differs from Jupiter's browns and oranges or Saturn's pale yellows. Neptune lies even farther out, orbiting at approximately 4.5 billion kilometers from the Sun, 30 times Earth's distance, and so far that sunlight takes over 4 hours to travel from the Sun's surface to reach the planet's cloud tops. The deep blue planet shows more atmospheric activity than Uranus, despite being farther from the Sun's heating. With visible dark storm systems and bright cloud features, indicating winds that reach speeds of over 2,000 kilometers per hour, the fastest planetary winds measured anywhere in the solar system. Neptune's blue color comes from methane absorption, like Uranus, but appears deeper and more vivid, possibly due to an unknown atmospheric component that enhances the blue beyond what methane alone would create. The planet completed its first full orbit since discovery in 2011, having traveled completely around the Sun once in the 165 years since astronomers first identified it in 1846, through mathematical predictions based on Uranus's orbital perturbations. The cold increases relentlessly this far from the Sun, with temperatures at Neptune's cloud tops averaging around minus 214 degrees Celsius, cold enough that nitrogen would freeze solid if it existed there. And methane remains a gas only because of the planet's internal heat and atmospheric pressure. The Sun appears as just a very bright star from this distance, its disk tiny and its warmth negligible, providing less than 1,000th the light intensity that Earth receives, and contributing almost nothing to heating Neptune's atmosphere compared to the heat rising from the planet's interior. You look back toward the inner solar system from Neptune's vicinity, seeing the Sun as a brilliant point surrounded by the planetary system compressed into a relatively small region of space. From this distant perspective, Earth invisible among the glare around the star. the entire inner system reduced to a faint glow against the darkness of space. Beyond Neptune lies the solar system's true frontier, the region where the Kuiper belt extends from Neptune's orbit outward to about 50 astronomical units from the Sun, populated by thousands of small icy bodies, including dwarf planets like Pluto, Eris, Makemake, and Haumea. These distant worlds orbit in the cold and dark, their surfaces covered in frozen nitrogen, methane, and water ice, their temperatures dropping to within a few degrees of absolute zero in the regions farthest from the Sun's faint warmth. Pluto itself orbits in this region, a world about 2,300 kilometers across, with a thin nitrogen atmosphere that freezes and falls to the surface as snow when Pluto's elliptical orbit carries it farther from the Sun, then sublimates back into gas when Pluto approaches perihelion, and solar heating increases slightly. You glimpse these distant objects only as faint points of light scattered across the outer darkness, the last substantial bodies before interstellar space begins. The giant planets fade behind you now as the spacecraft accelerates toward the solar system's edge. The massive worlds shrinking to bright points and then becoming indistinguishable from background stars as millions of kilometers expand into billions. You have passed through the Sun's planetary realm, from the hot inner system where rocky worlds orbit close to the star's radiation, through the asteroid belt where planet formation failed, past the gas giants Jupiter and Saturn with their complex moon systems and ring structures, beyond ice giants Uranus and Neptune, tilted and deep blue in the outer darkness, and now toward the boundary where the Sun's influence finally weakens and interstellar space begins. The solar system's architecture has revealed itself during this journey, the orderly arrangement of planets in their orbits, the way size and composition vary with distance from the Sun, the moons and rings and storms that make each world unique, despite sharing the same star as their gravitational anchor. Ahead lies the heliosphere's edge, and beyond that, the void between stars. The spacecraft travels outward beyond Neptune's orbit, entering the region where the solar system transitions gradually from a structured collection of planets and smaller bodies into the diffuse boundary zone where the Sun's influence weakens and interstellar space begins. This is not a sharp boundary, but a transition zone extending billions of kilometers, a region where the solar wind that streams outward from the Sun begins to slow and eventually stops its outward expansion as it encounters the pressure of the interstellar medium filling the space between stars. You are crossing through the heliosphere now, the vast bubble of charged particles and magnetic fields that the Sun creates around itself, a protective region that shields the inner solar system from some of the high-energy cosmic rays that permeate the galaxy beyond. The heliosphere extends outward from the Sun in a shape that depends on the solar wind's strength and the direction of the Sun's motion through the interstellar medium, creating an asymmetric bubble that stretches farther in the direction opposite the Sun's travel and compresses somewhat in the forward direction. The termination shock, where the solar wind suddenly slows from supersonic to subsonic speeds, occurs at varying distances depending on solar activity levels, but typically around 80 to 100 astronomical units from the Sun, roughly 2 or 3 times Neptune's orbital distance. Beyond the termination shock lies the heliosheath, a turbulent region where solar wind particles continue to flow outward but at reduced velocities, swirling and mixing in complex patterns as the sun's magnetic field compresses and the plasma density increases. The heliopause itself marks the true boundary where solar wind pressure balances the pressure of the interstellar medium, where particles from the sun meet particles from interstellar space in a dynamic boundary that shifts position as conditions change on both sides. Voyager 1 crossed the heliopause in August 2012 at a distance of about 121 astronomical units from the Sun, becoming the first human-made object to enter interstellar space, while Voyager 2 crossed in November 2018 at about 119 astronomical units, providing the first direct measurements of conditions beyond the heliosphere. Both spacecraft detected sudden changes in their instruments as they crossed, with the density of solar wind particles dropping almost to zero, while the density of interstellar particles increased correspondingly. And the direction of magnetic field lines changed from the spiral pattern created by the Sun's rotation to the straighter pattern of the galaxy's ambient field. Your spacecraft crosses the heliopause now, though you feel no sensation of the transition, no turbulence or impact, just a boundary in space, marked by changes in particle densities and field directions that instruments detect, but human senses cannot perceive. The temperature of the surrounding medium drops as you leave the heliosheath and enter interstellar space, the solar wind's heated particles no longer dominating the local environment, replaced by the colder interstellar plasma that fills the galaxy between stars. The particle density actually increases slightly beyond the heliopause, from about 3 to 5 particles per cubic centimeter in the heliosheath to about 7 particles per cubic centimeter in the local interstellar medium, though these numbers remain incredibly tiny compared to atmospheric densities, where particles number in the trillions per cubic centimeter at sea level on Earth. Cosmic ray intensity increases beyond the heliopause. The high-energy particles from distant supernovae and other energetic events in the galaxy now reaching your location with less shielding from the Sun's magnetic bubble. These cosmic rays consist primarily of protons moving at nearly the speed of light, accelerated by shock waves from exploding stars, or by magnetic fields near neutron stars and black holes, carrying energies far exceeding anything human particle accelerators can produce. The heliosphere blocks or deflects many lower energy cosmic rays, protecting the planets inside from some of this radiation, though higher energy cosmic rays penetrate the heliosphere regardless and contribute to the background radiation environment throughout the solar system, and indeed throughout the galaxy. Looking back toward the Sun from beyond the heliopause, you see the star as a very bright yellow-white point, brighter than any other star visible, but no longer appearing as a disk, too far away now for its surface details to resolve even with the spacecraft's windows. The planets have vanished from view entirely, their reflected light too faint to detect against the overwhelming glare of the Sun at this distance. The entire planetary system reduced to that single brilliant point, surrounded by darkness. Earth orbits somewhere in the invisible region around that point, a world you left behind when this journey began, now utterly lost in the Sun's light, its existence known, but its location impossible to pick out. From millions of kilometers away, where no telescope aboard this spacecraft could separate the planet's faint reflection from the star's overwhelming Brightness. The sun remains the brightest object in your sky, despite the vast distance, shining with an apparent magnitude of about -18 from 120 astronomical units away. Still far brighter than the full moon appears from Earth, but no longer the overwhelming presence it represented in the inner solar system. The star's light continues to dominate illumination in your immediate vicinity, still providing enough photons that you can see by its light alone. Though the intensity has dropped to about 1/10,000th of what Earth receives and continues diminishing with increasing distance. Eventually, after traveling hundreds or thousands of astronomical units farther, the sun will fade to just another bright star among many, indistinguishable in brightness from Sirius or Canopus or other luminous stars scattered across the galaxy. Just one more point in the vast scatter of starlight. The interstellar medium surrounds you now, the thin gas and dust that fills the space between stars throughout the galaxy's disk. Composed primarily of hydrogen, with about 9% helium, and traces of heavier elements created in previous generations of stars and distributed into space when those stars died. The local interstellar cloud through which the solar system currently moves has a temperature of about 6,000 degrees Celsius. Though this temperature reflects the average kinetic energy of individual atoms, rather than what humans experience as heat, since the density is so low that collisions between particles happen infrequently and cannot transfer significant thermal energy to solid objects. The cloud's density averages about 0.3 atoms per cubic centimeter, an incredibly tenuous medium that qualifies as excellent vacuum by terrestrial laboratory standards, but represents typical or even slightly dense conditions for interstellar space. Dust grains drift through the interstellar medium, solid particles typically about 1/10 of a micrometer across, small enough that 1,000 lined up would span the width of a human hair, composed of carbon or silicate minerals or ice, depending on local conditions and the history of the material. These tiny particles scatter and absorb starlight, creating the extinction effect that dims distant stars and makes the galaxy's disk appear darker when viewed edge-on, the dust concentrating in the galactic plane and blocking light from stars on the far side of the disk. The particles themselves originated in the atmospheres of evolved stars, where elements heavier than helium condense into solid form and get expelled into space by stellar winds or supernova explosions, seeding the interstellar medium with the raw materials that will eventually participate in forming the next generation of stars and planetary systems. Stars surround you in all directions now, no longer hidden behind the sun's glare or the sky's brightness, but scattered across the complete sphere of space surrounding the spacecraft. Some appear brighter because they lie closer in three-dimensional space, their light taking only a few years to reach you, rather than decades or centuries required for more distant stars. Others appear bright because they genuinely emit more light than average. Massive hot stars that burn through their fuel quickly, but shine with luminosities thousands or millions of times the sun's output during their brief lives. The Milky Way band stretches across the sky as a luminous river of light, the combined glow of billions of stars too distant to distinguish individually, concentrated in the flat disk of the galaxy that you are now preparing to cross on your journey towards its center. The perspective shift feels profound, even though nothing dramatic marks the crossing of the heliopause. No barrier or wall or sudden change in appearance. Just the recognition that you have left the sun's domain and entered the realm between stars. The solar system lies behind you now, a structure centered on one ordinary star, containing 8 major planets and dozens of moons and millions of smaller bodies, all held together by the sun's gravity and illuminated by its light, all orbiting in the pattern established 4.5 billion years ago when the system formed. You are no longer part of that structure, no longer orbiting the sun in any meaningful sense, your velocity carrying you away from the star faster than its gravity can pull you back, escaping into the larger galaxy beyond. The nearest stars lie ahead at distances measured in light years rather than astronomical units, with Proxima Centauri the closest at about 4.2 light years from the Sun, followed by the binary pair Alpha Centauri A and B at slightly greater distance. These stars appear as bright points in the southern celestial hemisphere from the Sun's perspective. Among the closest stellar neighbors, but still separated by such enormous distances that light itself requires years to cross the gap, and conventional spacecraft would need tens of thousands of years to make the journey. Your faster-than-light velocity compresses this travel time dramatically, allowing the journey to continue across interstellar distances in hours or days rather than millennia. Though the vast scales remain conceptually overwhelming, even with this advanced propulsion technology, interstellar space stretches ahead for thousands of light years in every direction. The region containing hundreds of billions of stars organized into the Milky Way's disk and bulge structure, all orbiting the galactic center, where something massive anchors the entire system's rotation. You are beginning that journey now, leaving the sun behind, entering the darkness between stars, crossing the first steps of a path that will carry you through stellar neighborhoods and spiral arms, past clouds of gas and dust where new stars form, eventually reaching the dense regions near the galaxy's heart, where stars pack together far more tightly than they do in this outer region. The sun fades slowly behind you as the spacecraft accelerates along its trajectory, one star becoming indistinguishable among countless others, while ahead the path leads deeper into the galaxy, toward regions unknown and wonders unimagined from Earth's distant surface. The transition feels complete now, the solar system definitely behind you, interstellar space definitely surrounding you. The journey's next phase beginning as you move into the realm where stars separate by light years, and where the sun's influence becomes negligible compared to the collective gravity of the galaxy's stellar population. You have crossed the boundary, left the familiar for the unknown, exchanged the structured solar environment for the diffuse interstellar medium. And now the real journey begins, the crossing of the galaxy from its outer regions to its bright center, through the spaces between suns and the clouds where starlight scatters, across distances that light measures in years and millennia toward the ultimate destination waiting, 26,000 light years ahead, where the Milky Way's heart beats in the darkness. The spacecraft travels through the interstellar medium now, the thin substance that fills the space between stars throughout the galaxy's disk and halo, a region that appears empty to human senses, but contains enough material to affect light and shape the galaxy's structure. You peer into the darkness surrounding the spacecraft, seeing starlight from all directions, but no clear sign of the medium itself. The gas and dust, too tenuous to scatter enough light to become visible as glowing nebulosity, unless concentrated in denser clouds or illuminated by nearby bright stars. The medium exists nonetheless, detected by instruments that measure particle densities and magnetic field strengths and radiation wavelengths, revealing the invisible substance through which you now pass on this journey across the galaxy. Hydrogen dominates the interstellar medium's composition, making up about 70% of its mass, existing mostly in atomic form in warmer regions and molecular form in colder, denser clouds, with some areas ionized by ultraviolet radiation from hot stars. Helium comprises most of the remaining mass at about 28%, while heavier elements like carbon, nitrogen, oxygen, and iron contribute about 2% of the total. All these heavier elements created inside stars and distributed into space when those stars reach the end of their lives. The temperature of the medium varies enormously, depending on location and local conditions. From about 10 degrees above absolute zero in the densest molecular clouds to over 1 million degrees in hot bubbles created by supernova explosions, with the average temperature in most regions around 8,000 degrees, despite the incredibly low density. The density varies as dramatically as the temperature, with typical values in diffuse regions around 0.1 to 1 atom per cubic centimeter, rising to hundreds or thousands of atoms per cubic centimeter in molecular clouds, and dropping to below 0.001 atoms per cubic centimeter in the hot, low-density bubbles excavated by stellar winds and supernova shock waves. Even the densest molecular clouds remain far more rarefied than Earth's atmosphere, where particle density exceeds 2 × 10 to the 19th power per cubic centimeter at sea level, making even the densest interstellar regions qualify as excellent vacuum by terrestrial standards. The extreme thinness of the medium means that spacecraft traveling through it encounters essentially no resistance or friction, no drag that would slow the vessel or heat its surface, just occasional impacts from individual atoms or dust grains that pose minimal threat at any reasonable travel velocity. Dust grains drift through the medium alongside the gas-solid particles that formed in the atmospheres of dying stars, or in the debris clouds from supernovae, composed of silicate minerals, carbon compounds, or water ice, depending on the grain's formation, environment, and history. The typical grain measures about 1/10 to 1 micrometer across, large enough to scatter visible light effectively, but small enough to remain suspended in the thin gas and carried along by gas motions without settling out under gravity. These particles number about 1 grain per trillion atoms of gas, a tiny fraction of the total medium mass, but significant enough to affect observations, scattering and absorbing starlight, and creating the dark lanes visible in images of the Milky Way, where dust concentrations block background stars from view. The local interstellar cloud through which the solar system currently moves extends for several light years in all directions. A relatively low-density region with temperatures around 6,000 degrees and densities around 0.3 atoms per cubic centimeter. Part of the larger local bubble structure that may have formed from ancient supernova explosions, clearing out a cavity in the denser disk material. This cloud represents just one small structure among countless similar clouds and bubbles and filaments that fill the interstellar medium throughout the galaxy. Regions with slightly different temperatures and densities than their surroundings, created by stellar winds and radiation and explosions, and then slowly dispersing and mixing back into the general medium over millions of years. The cloud shows no distinct boundary, just gradual transitions into neighboring regions with slightly different properties, the whole medium structured and dynamic rather than uniform and static. Magnetic fields thread through the interstellar medium, invisible lines of force that guide charged particles and shape the distribution of ionized gas, with typical field strengths about 1/1,000,000th the strength of Earth's surface magnetic field, but spanning such enormous volumes that their total energy content becomes significant. The fields align roughly with the spiral arms, following the galaxy's rotation and the flow patterns of gas moving through the disk, creating a large-scale structure that influences how cosmic rays propagate and how gas clouds collapse to form new stars. Charged particles spiral along these field lines, rather than moving freely in straight paths, their motion constrained by the magnetic force that deflects them perpendicular to their velocity, creating a coupling between the magnetic field and the ionized component of the gas. Stars appear scattered through the darkness in all directions, each one separated from its neighbors by light years of this thin medium, each shining with light that has traveled through space for years or decades or centuries before reaching your current position. The nearest stars lie several light years away, their light arriving after multi-year journeys through the medium during which some photons scattered off dust grains or got absorbed by gas atoms, while others traveled undisturbed across the full distance. More distant stars packed together in the Milky Way band, too far away to distinguish individually without powerful magnification. Their combined light creating the luminous glow that marks the galactic disk's position in the sky, brighter toward the galactic center direction and dimmer toward the outer edge. The Milky Way band shows structure as you study it more carefully. Bright regions and dark regions alternating along its length, the variations created by dust clouds that block background starlight and appear as dark lanes against the brighter regions where fewer dust concentrations allow more stars to shine through. The Great Rift runs along the Milky Way through the Cygnus region, a dark lane caused by overlapping dust clouds between the Sun and the galaxy center, blocking direct optical views of the inner galaxy and requiring infrared or radio observations to see through the obscuration. Other dark patches appear throughout the band, each one marking a dust cloud or molecular cloud complex, positioned between your location and the more distant stars beyond. Evidence that the interstellar medium clumps and concentrates rather than spreading uniformly through space. Nebulae appear in certain directions, where dense gas clouds glow from internal illumination or scattered light, visible as faint patches of light, distinguishable from the point sources that mark individual stars. Emission nebulae glow red and pink from hydrogen atoms excited by ultraviolet radiation from hot young stars. The atoms absorbing high-energy photons and then re-emitting that energy as visible light at specific wavelengths characteristic of hydrogen's electron transitions. Reflection nebulae appear blue from starlight scattering off dust grains. The blue color occurring because shorter wavelengths scatter more efficiently than longer wavelengths, just as Earth's atmosphere scatters blue light and creates the daytime sky color. Some nebulae combine emission and reflection, glowing red from excited hydrogen while reflecting blue light from nearby stars, creating colorful structures visible across many light years of space. The darkness between stars appears complete in most directions. No glowing gas or scattered light bright enough to detect without sensitive instruments. Just the black of space, interrupted only by stellar points and the subtle Milky Way band. This darkness represents the normal state of interstellar space, the typical environment that exists throughout the galaxy's volume, except in the special locations where gas density reaches high enough levels to produce visible nebulosity. The emptiness feels profound, despite knowing that atoms and dust grains do exist here in small numbers. Their presence real, but their density so low that they create no visible effect, no fog or haze or glow. Just transparency, broken only by the occasional dust grain blocking a single photon from a distant star. Time passes differently on this journey through interstellar space than it did while traveling through the solar system, where planets and moons provided distinct waypoints and visible destinations to mark progress and measure distance traveled. Here, in the void between stars, motion continues at velocities exceeding light speed, but landmarks appear rarely. Perhaps an occasional nebula or a close approach to another star, but mostly just the slow shifting of stellar positions as your position changes relative to their locations. Light years accumulate as the journey continues, distance from the sun increasing steadily, while distance to the galactic center decreases incrementally. The progress measurable by instruments, but not immediately apparent to casual observation, where the star field changes only gradually over long travel times. The spacecraft moves through a region containing roughly 1 star per cubic parsec, on average, though the distribution varies with position in the galaxy's disk and proximity to spiral arm concentrations. A parsec spans about 3.26 light-years, so 1 star per cubic parsec translates to typical stellar separations of several light-years, with variations where stars cluster more tightly in groups or spread more widely in the gaps between spiral arms. This spacing means that close stellar encounters happen rarely, with most stars maintaining their distances from neighbors over millions of years, moving in roughly parallel orbits around the galactic center, rather than frequently approaching or departing from nearby stars. The local stellar neighborhood around the Sun contains about 340 stars within 33 light-years, giving an average density slightly less than 1 per cubic parsec, typical of this region in the galaxy's disk. Cosmic rays continue to impact the spacecraft at rates higher than they did inside the heliosphere. The energetic particles arriving from all directions across the galaxy and from beyond, some accelerated by supernova shockwaves within the Milky Way, while others originated in distant galaxies and traveled for millions of years before reaching this location. The highest energy cosmic rays carry energies exceeding 10 to the 20th power electron volts, energies so high that their origin remains uncertain, possibly created in the jets from supermassive black holes or in other extreme environments where magnetic fields and shock waves can accelerate particles to these remarkable velocities. The spacecraft's shielding protects against most cosmic ray impacts, absorbing or deflecting the particles before they can reach occupied compartments. Though the radiation environment in deep space remains challenging and requires constant monitoring to ensure safety, the journey continues through this ocean of thin gas and scattered dust, through the invisible substance that fills the galaxy's volume and provides the raw material from which new stars will eventually form when the medium concentrates enough to trigger gravitational collapse. You are traveling through the construction material of future solar systems, atoms that will someday participate in building planets and moons and perhaps living organisms. But for now, these atoms drift freely through space, unbound and uncollected, part of the diffuse medium that represents matter's normal state between the brief intervals when it aggregates into stars and planets. The darkness stretches ahead for thousands of light years, the void between suns that you must cross to reach the galaxy's heart, and the spacecraft moves steadily forward through that darkness, carrying you deeper into the Milky Way structure, toward regions where stars appear more frequently and where the galaxy's spiral pattern begins to reveal itself in the organization of stellar populations. Stars begin appearing more frequently as the journey carries you deeper into the galaxy's disk, the stellar density increasing gradually as you move inward from the sun's position toward regions where stars concentrate more tightly and where the average distance between neighbors shrinks from light years to slightly smaller fractions of light years. The first star you approach closely enough to see as more than just a point appears reddish-orange in color, smaller and dimmer than the sun, one of the galaxy's most common stellar types, known to astronomers as red dwarfs or M-type stars. This star measures perhaps 1/3 the sun's diameter and contains about 20% of its mass, burning hydrogen in its core at a much slower rate that allows it to maintain stable energy output for trillions of years, far longer than the sun's 10 billion-year main sequence lifetime. The red dwarf's surface glows at a temperature around 3,000 degrees Celsius, cool compared to the sun's 5,500 degrees, the lower temperature shifting its light output toward red and infrared wavelengths, rather than the yellow and white light the sun emits. You can see the star's disk now, as the spacecraft passes within a few light months of its position, the surface showing darker spots where magnetic fields suppress convection, and lighter regions where hot plasma rises from the interior, similar to the sun's sunspots, and bright faculae, but appearing different in color due to the cooler overall temperature. The star's light casts an unfamiliar reddish tint over everything it illuminates, creating shadows that appear less harsh than under the sun's brighter light. The dimness and color making the environment feel alien, despite the same physical processes occurring in this star as in the sun. Planets likely orbit this red dwarf, though none are immediately visible from your trajectory. Small worlds perhaps huddling close to the star, where temperatures allow liquid water, despite the dim light. Their orbits measured in days or weeks, rather than the months and years that terrestrial planets require to circle the sun. Red dwarfs make up about 75% of all stars in the galaxy, their abundance meaning that most stars are actually dimmer and smaller than the sun, rather than larger and brighter. Though their low luminosity makes them invisible to the naked eye from interstellar distances and prevents them from contributing significantly to the Milky Way's total light output. This particular red dwarf will continue fusing hydrogen for several trillion years, outlasting the sun by a factor of hundreds, still shining long after the Milky Way and Andromeda have merged, and the universe has expanded to many times its current size. The spacecraft continues onward, leaving the red dwarf behind as the journey proceeds deeper into the galactic disk, and another star appears ahead after covering several more light years of distance. This star appears yellow and immediately familiar, a spectral type similar to the sun, what astronomers classify as a G-type main sequence star burning hydrogen in its core. and shining with steady light that has remained nearly constant for billions of years. The star's surface temperature matches the sun's within a few hundred degrees. Its mass falls within 10% of the sun's mass, and its diameter spans almost exactly the same 190,000 kilometers that the sun measures, making this star essentially a solar twin located hundreds of light years from where the sun orbits the galactic center. Observing this sun-like star from a distance of several light weeks shows you what an alien observer might see when looking at the sun from another stellar system. The star appearing as a bright yellow-white point with a steady luminosity and no obvious unusual features to distinguish it from billions of similar stars scattered throughout the galaxy. A planetary system might orbit this star just as planets orbit the sun, perhaps including a rocky world at the right distance to maintain liquid water on its surface, maybe supporting life that looks upward at night and wanders about the stars scattered across their sky, including perhaps the distant speck that is our sun. The possibility remains unconfirmed from your current trajectory, but statistics suggest that most sun-like stars host planetary systems with at least a few worlds in various orbits. The process of planet formation appearing to be a common outcome when stars form from collapsing clouds of gas and dust. The stellar variety continues to reveal itself as you travel through this region of the galaxy's disk. The next star encountered appearing as a binary system, where two stars orbit their common center of mass in a gravitational dance that has persisted for billions of years. The brighter component shines yellow-orange, perhaps slightly cooler and less massive than the sun, while its companion glows dimmer and redder. A smaller star that contributes perhaps 30% of the system's total light output. The two stars circle each other at a separation of about 40 astronomical units, similar to the distance between the Sun and Pluto, completing one mutual orbit every few decades as they both continue orbiting the galactic center together as a bound pair. Binary star systems make up perhaps half of all stellar systems in the galaxy, with many stars possessing companions rather than existing alone like the Sun. The pairing created when molecular clouds fragment during collapse and form multiple cores that each develop into separate stars while remaining gravitationally bound. Some binaries orbit close together, with periods measured in hours or days, so close that material can transfer between the stars if one expands during evolution, while other binaries separate by thousands of astronomical units and take tens of thousands of years to complete their mutual orbits. This particular pair represents an intermediate case, close enough to clearly orbit each other over human timescales, but separated enough that each star evolves independently, without significant interaction between them, at least for now, while both remain on the main sequence, burning hydrogen in their cores. The spacecraft's path carries you near a very different type of stellar object, a white dwarf that represents the final state of stars like the Sun after they exhaust their nuclear fuel and shed their outer layers into space. This white dwarf appears as a tiny but intensely bright point, its surface heated to about 20,000 degrees Celsius and glowing blue-white, far hotter than the Sun, despite the white dwarf containing no ongoing fusion reactions to generate new energy. The star measures only about 12,000 kilometers across, roughly Earth's diameter, but contains about 60% of the Sun's mass, compressed into that small volume, creating a density of approximately 1 million grams per cubic centimeter, where a teaspoon of material would weigh several tons at Earth's surface gravity. The white dwarf shines from stored thermal energy, gradually cooling over billions of years as it radiates heat into space, without any fusion process to replace the lost energy, eventually destined to fade to a cold, dark cinder called a black dwarf, though the universe remains too young for any white dwarfs to have cooled completely to that final state. The surface shows no features, no spots or prominences or activity, just a smooth sphere of carbon and oxygen nuclei packed tightly together with electrons forming a degenerate gas that provides pressure support against gravitational collapse. This particular white dwarf may have formed 1 billion years ago when its parent star exhausted its core hydrogen, expanded into a red giant, and then shed its outer layers as a planetary nebula, while the core collapsed into the dense remnant you now observe. The entire evolution from main sequence star to white dwarf taking place long before humans evolved on distant Earth. A young hot star appears in a different region of sky, blue-white and brilliant, shining with a luminosity thousands of times the sun's output, despite forming relatively recently in astronomical terms. This O-type star burns hydrogen at a ferocious rate, fusing its core fuel so quickly that it will exhaust its energy supply in only a few million years, rather than the billions of years that cooler stars like the Sun enjoy, living fast and bright before ending in a supernova explosion that will scatter its material back into the interstellar medium. The star's surface temperature exceeds 30,000 degrees Celsius, hot enough that most of its light emerges in ultraviolet wavelengths rather than visible light, the intense radiation ionizing gas for dozens of light years around the star, and creating a region of glowing plasma called an emission nebula. The blue star's mass probably exceeds 20 solar masses, enough that radiation pressure from the intense light output pushes outward on the outer layers and creates a powerful stellar wind that carries away material at speeds of thousands of kilometers per second, stripping away a significant fraction of the star's mass over its brief lifetime. Stars this massive and hot are rare, making up less than 1% of the stellar population, but their high luminosity makes them visible across enormous distances and gives them disproportionate influence on their surrounding environments, shaping and heating the interstellar medium and triggering new star formation in nearby clouds through compression from their winds and eventual supernova shockwaves. This star likely formed within the last million years, part of a young cluster where dozens or hundreds of stars emerged from the same parent molecular cloud and now orbit through the galaxy as a loose group that will gradually disperse over tens of millions of years. The variety among stars becomes increasingly apparent as you continue past more examples of different stellar types, each one representing a different mass, different temperature, different evolutionary stage, different fate, awaiting it billions or millions of years in the future. Orange K-type stars appear occasionally, intermediate between the Sun's yellow and the red dwarf's deep orange, living longer than the Sun, but shorter than red dwarfs, making up about 12% of all stars and hosting many confirmed planets in their habitable zones. Giant stars appear in the distance, evolved stars that have exhausted their core hydrogen and expanded to enormous sizes while cooling to orange or red surface temperatures. Each one destined to either fade as a white dwarf if its mass remains below 8 solar masses, or explode as a supernova if its mass exceeds that threshold. The stellar population reveals the galaxy's history as you observe star after star, each one containing clues about when it formed and what materials were available in the interstellar medium at that time. Older stars contain fewer heavy elements because they formed early in the galaxy's history when only hydrogen and helium existed in significant quantities. The first stars creating carbon and oxygen and iron through fusion and distributing those elements into space when they died. Younger stars contain more heavy elements, their spectra showing absorption lines from dozens of elements heavier than helium, evidence that they formed from gas already enriched by previous stellar generations. What astronomers call metals in terminology, where anything heavier than helium qualifies as a metal regardless of its chemical properties on the periodic table. The Sun sits somewhere in the middle of this metal enrichment scale, containing enough heavy elements to suggest it formed about 4.6 billion years ago from gas that had been cycled through several previous generations of stars, but not so metal-rich as the youngest stars forming today from gas enriched by many more stellar generations. Each star you pass carries this chemical fingerprint, its spectrum revealing its metallicity and thus constraining its age. The older metal-poor stars appearing yellow or orange or red, while the youngest metal-rich stars tend toward blue or white as more massive stars able to form from more efficiently cooling gas clouds. The galaxy's stellar population thus shows an age distribution, with the oldest stars formed 10 billion years ago or more, and the youngest stars currently emerging from molecular clouds, the star formation process continuing today, just as it has throughout galactic history. The journey through this stellar neighborhood has carried you past dozens of stars, each one unique, but also representative of stellar types found throughout the galaxy's disk population. The samples showing what exists in the Milky Way's stellar census, from the most common dim red dwarfs to the rare massive blue giants, and everything in between. Stars continue to appear ahead as the trajectory carries you deeper into the disk, where stellar density increases and stars pack more closely together. The frequency of encounters rising from one star every few light years to more stars visible simultaneously as the background population grows denser. Ahead lies the spiral arm structure, where stars concentrate even more tightly in lanes marking density waves, where molecular clouds harbor new star formation, and where the galaxy's architecture becomes visible in the organization of stellar populations and interstellar material. The spacecraft enters a region where stars appear noticeably more concentrated than in the sparse neighborhood around the Sun's position, the stellar density rising as you cross into the Orion Spur, a minor spiral arm connecting the larger Perseus and Sagittarius arms that shape the Milky Way's overall structure. The increase in stellar frequency becomes apparent as you look ahead, seeing dozens of bright points scattered across the view, where previously only a handful appeared. The concentration not dramatic, but clearly higher than the baseline density in the interarm regions you have been crossing. This is one of the galaxy's organizational features revealing itself. The way stars and gas organize into lanes and concentrations, rather than spreading uniformly through the disk. the spiral pattern that gives the Milky Way its overall shape when viewed from outside. Spiral arms function as density waves rather than fixed structures, regions where stars and gas and dust temporarily concentrate as they orbit through the galaxy, slowing slightly as they enter the arm and then speeding up again as they leave, spending more time in the arm region and thus creating a persistent concentration despite individual stars constantly entering and leaving. The Sun itself orbits through spiral arms over hundreds of millions of years, currently residing in the Orion Spur, but having passed through other arms in the distant past and destined to enter other arms in the future as the galaxy's rotation carries it around the galactic center. The arms persist because the density wave propagates around the galaxy at a different rate than the star's orbit. The wave pattern rotating more slowly and creating regions where stellar orbits bunch together gravitationally, similar to how traffic jams can persist on highways, even though individual cars constantly flow through the congested region. Young hot stars dominate the spiral arm's visible appearance, their blue-white light shining brightly and making the arms stand out in images of spiral galaxies, even though most of the stellar mass consists of older, dimmer stars, invisible at great distances. These massive stars form preferentially in spiral arms, where gas densities reach high enough levels to trigger collapse and star formation. The compression from the density wave pushing molecular clouds beyond their stability threshold and causing them to fragment into cores that each form new stars. The massive stars burn bright and die young, exploding as supernovae after only a few million years, so they remain close to their birthplaces in the spiral arms and create the blue color that highlights the arms in galaxy images. Lower mass stars also form in the arms, but live much longer and gradually drift away from their birth locations, spreading throughout the disk and contributing to the background stellar population, visible everywhere rather than concentrated in the arms. Nebulae appear in the spiral arm region, glowing clouds of gas, illuminated by the hot young stars that formed within them. The massive star's ultraviolet radiation ionizing surrounding hydrogen and causing it to emit the characteristic red light visible in emission nebulae. One nebula appears particularly prominent in your view, a vast cloud stretching across dozens of light years, glowing red and pink from hydrogen emission, with hints of green from oxygen atoms, and blue regions where starlight scatters off dust particles embedded in the gas. The cloud's structure shows intricate detail, with bright knots where gas concentrates more densely, dark lanes where dust blocks the background glow, and wispy filaments extending outward where stellar winds and radiation pressure sculpt the cloud into complex shapes and drive material away from the central star-forming regions. The Orion Nebula serves as a prime example of these star-forming regions, though whether you encounter that specific nebula depends on your trajectory through this section of the arm, the principle remaining the same, regardless of which particular nebula appears in your windows. Young stars embedded in the cloud shine brilliantly despite their youth. Some still surrounded by dusty disks where planets might be forming. Others already cleared of their birth material and beginning their billions of years of steady main sequence fusion. The most massive stars in the cluster, perhaps a few dozen times the Sun's mass, pump enormous amounts of ultraviolet radiation into the surrounding gas, creating the ionization that makes the cloud glow and gradually dispersing the cloud through radiation pressure and stellar winds that push gas outward against the gravity, trying to hold it together. Dark nebulae appear as well, molecular clouds where no internal illumination exists, and where the only visible effect comes from foreground dust blocking background starlight, creating dark patches and lanes against the brighter regions behind them. These clouds contain the coldest, densest gas in the interstellar medium, with temperatures dropping to perhaps 10 degrees above absolute zero, and densities reaching thousands or tens of thousands of molecules per cubic centimeter. Still incredibly thin by terrestrial standards, but dense enough that gravity begins to dominate over pressure support and trigger collapse. New stars form in these dark clouds, the densest regions fragmenting and contracting, until temperatures and pressures in their cores reach the thresholds for fusion ignition, lighting up new suns that will eventually disperse their parent clouds and emerge as visible stars, joining the galaxy's population. Dust lanes thread through the spiral arm region, long filaments of dark material stretching across light years of space, visible only as shadows against brighter backgrounds or as reddening of starlight that passes through them before reaching your position. The dust grains scatter blue light more efficiently than red, so stars seen through dusty regions appear redder than their actual colors, the amount of reddening indicating how much dust lies along the line of sight, and allowing astronomers to map dust distribution even when the dust itself remains invisible. The spiral arms contain more dust than inter-arm regions, because dust and gas trace the same density waves that concentrate stars, the dust originating from stellar winds and supernovae that inject carbon and silicate particles into the interstellar medium, where they survive for hundreds of millions of years before getting incorporated into new stars or destroyed by shock waves. Star clusters appear embedded in the spiral arm structure. Groups of stars born together from the same molecular cloud and still orbiting through space as loose associations that will gradually disperse over tens or hundreds of millions of years. Open clusters contain anywhere from dozens to thousands of stars, all roughly the same age and chemical composition since they formed from the same parent cloud. Their tight grouping making them stand out against the background stellar population. One cluster appears in your path, perhaps 500 stars concentrated into a region about 10 light years across, all blue or white in color indicating youth and high mass. The cluster age, probably only a few million years, based on the presence of such short-lived massive stars still burning in the group. The cluster's stars orbit their common center of mass in a complex gravitational dance, each star moving on its own trajectory, but bound to the group by the collective gravity of all members, creating a dynamical system that remains stable as long as no external perturbations disrupt the delicate balance. Over time, encounters with molecular clouds or the gravitational tides from the galaxy's disk will strip away the cluster's outer members, gradually dissolving the association until individual stars spread across the galactic disk with nothing to mark their common origin except their identical ages and compositions. Some clusters survive longer than others, depending on their initial mass and density, with the most massive clusters remaining, bound for 1 billion years or more, while looser associations disperse within a few million years. The Orion spur extends for thousands of light years through the galaxy's disk, a substantial structure though smaller than the major Perseus and Sagittarius arms it connects, containing millions of stars and thousands of molecular clouds and hundreds of active star-forming regions where new stellar generations continued to emerge. The spur formed through density wave resonances and gravitational interactions between the major arms, creating a connecting feature that appears in many spiral galaxies as minor arms linking the dominant structures. You are traveling through this minor arm now, seeing its enhanced stellar density and active star formation, observing the nebulae and clusters that characterize spiral arm regions, experiencing the organized structure that makes spiral galaxies appear as beautiful pinwheel shapes when viewed from outside, rather than featureless disks of uniformly distributed stars. The transition through the spiral arm feels gradual, the stellar density rising slowly as you entered, and now beginning to decline slowly as you approach the arm's far side. No sharp boundaries marking where the arm begins or ends, but rather smooth variations in star and gas concentrations that peak in the arm's center and decline toward its edges. The journey has revealed the arm's character, the way it concentrates young stars and glowing gas and dark dust into a lane stretching around the galaxy's disk. A structure created by gravitational organization rather than physical barriers, persistent despite all its constituent stars and gas, constantly moving through the region rather than remaining stationary. The galaxy reveals its architecture through these features, showing you the large-scale pattern that individual stars within cannot perceive, the spiral shape that requires distance and perspective to recognize. Temperature varies throughout the spiral arm, depending on proximity to hot stars and supernova remnants, with some regions heated to thousands or tens of thousands of degrees by ultraviolet radiation, while other regions remain cold and dark in the shielded interiors of molecular clouds. The hot ionized regions expand as bubbles and shells driven by stellar winds and explosions, compressing surrounding gas and potentially triggering new episodes of star formation in the compressed material, creating feedback loops where star formation begets more star formation in a self-propagating process. Eventually, the spiral arm will pass beyond this region as the density wave continues rotating around the galaxy, and the enhanced star formation will decline as gas densities drop below critical thresholds. The current star-forming regions fading and dispersing, while new regions light up in the arm's new position millions of years in the future. The spacecraft continues across the arm toward its far edge, the stellar density beginning to decline as you approach the inter-arm region beyond. The frequency of bright blue stars decreasing as you leave the zone of active star formation and enter regions dominated by older stellar populations. Ahead lies the next section of the journey, crossing the gap between the Orion Spur and the inner galaxy regions, where stellar density rises again, not from spiral arm concentration, but from proximity to the galactic center, where the overall stellar population grows denser. The Orion Spur fades behind you now, its young clusters and glowing nebulae receding into the distance, its enhanced stellar density giving way to the sparser inter-arm environment. The journey continuing inward across the galactic disk, toward the bulge and core regions that wait thousands of light years ahead, where the galaxy's true center lies hidden among billions of older stars, packed into the smallest central volumes. The spacecraft travels through regions where the stellar density increases gradually but persistently, The frequency of stars rising not from temporary spiral arm concentration, but from proximity to the galaxy's inner regions, where the overall stellar population grows denser with decreasing distance from the galactic center. You notice more stars visible simultaneously in all directions, the average separation between neighboring suns decreasing from the light years that characterized the solar neighborhood to distances measured more comfortably in smaller units, the stellar environment becoming noticeably more populated as your journey continues inward. The view through any window shows dozens of stars bright enough to stand out individually against the background glow. Their colors ranging from blue-white through yellow and orange to deep red, each representing a different stellar type and evolutionary stage. This increase feels gradual rather than sudden, a slow accumulation of stellar presence that builds naturally over the thousands of light years you traverse, the galaxy revealing its denser inner architecture through patient observation rather than dramatic transition. The character of the stellar population shifts alongside the density increase, the proportion of hot, young blue stars declining, while older orange and red stars become more common in your field of view. These cooler stars represent earlier generations, suns that formed billions of years ago, when the galaxy itself was younger, and the inner regions experienced their most intense periods of star formation. Many appear as red giants, evolved stars that have exhausted the hydrogen fuel in their cores and expanded to enormous sizes. Their surfaces cooler than they were during their main sequence lives, but their total luminosity increased by their sheer scale. You pass within a few light years of one such giant, its orange-red disk, visibly larger than most stars even at this distance. Its diffuse outer atmosphere, extending far beyond where a normal star's surface would end. The entire structure representing a sun in the late stages of its life cycle, slowly shedding material into the surrounding space. The prevalence of these older stars reflects the history of star formation in the inner galaxy. Regions that converted much of their available gas into stars during the Milky Way's early history, and now contain populations dominated by stars several billion years old. The initial burst of star formation that occurred when the galaxy first assembled created generations of massive stars that lived fast and died young. Their supernova explosions, enriching the surrounding gas with heavy elements that became incorporated into subsequent stellar generations. The stars you see now formed from that enriched material, their composition containing higher proportions of elements heavier than hydrogen and helium compared to stars in the outer galaxy, where less prior star formation had occurred. This difference in metallicity, as astronomers call it, affects stellar evolution in subtle ways, with higher metallicity stars developing slightly different internal structures and exhibiting somewhat different behaviors during their lives. Gas and dust appear less prominent here than in the spiral arms you traversed earlier. The raw material for new star formation largely depleted by billions of years of converting interstellar clouds into stars. The nebulae that glowed in vibrant reds and blues along the spiral arms appear rarely in these inner regions, their absence creating a cleaner view of the stellar population without the obscuring dust lanes and emission regions that complicated observations in the galactic disk's younger zones. What gas remains exists in thin, diffuse clouds or in material shed by dying stars, like the red giant you recently passed. The stellar winds and planetary nebulae from evolved stars adding small amounts of gas back into the interstellar medium, but insufficient to fuel significant new star formation. The environment feels older and more settled. The chaotic activity of stellar birth giving way to the quieter processes of stellar aging and death. The inner galaxy's star-forming days largely behind it, while the outer regions continue producing new suns in abundance. You begin noticing objects above and below the galactic disk's plane, spherical concentrations of light that hang in the space perpendicular to the flat distribution of disk stars. These globular clusters represent some of the oldest structures in the galaxy, dense balls of stars that orbit through the galactic halo, passing through the disk plane periodically during their long elliptical orbits around the galactic center. Each cluster contains hundreds of thousands of stars packed into a volume only a few dozen light-years across, creating stellar densities far exceeding anything found in the disk regions where stars like our Sun reside. From your current position, the nearest globular cluster appears as a fuzzy sphere of light, individual stars visible around its edges, while the central regions blend into a continuous glow where stellar separations become too small to resolve from this distance. The stars within globular clusters formed together very early in the galaxy's history, condensing from a single large cloud of gas more than 12 billion years ago, when the Milky Way itself was still assembling. Their extreme age means these clusters contain no young blue stars, all the massive hot stars that formed initially, having long since exhausted their fuel and died, leaving behind populations dominated by lower mass stars in various stages of evolution. The clusters orbit through the galactic halo in paths that differ dramatically from the orderly circular orbits of disk stars. Their trajectories, carrying them far above and below the galactic plane in elongated ellipses that reflect the conditions present when they formed, before the rotating disk had fully organized itself. Watching a globular cluster drift slowly across your field of view gives you a sense of the galaxy's three-dimensional structure. The disk, representing only one component of a larger system that includes the stellar halo surrounding it. The view of the Milky Way band itself changes from your new vantage point deeper within the galaxy's structure. The familiar river of light that stretched across Earth's night sky, now appearing different when observed from a position thousands of light-years closer to the galactic center. Looking outward toward the galaxy's edge, you see the spiral arms and outer disk regions as a band of light that encircles you. Though dimmer than from Earth due to the intervening dust and the sheer number of foreground stars blocking and absorbing light from more distant regions, looking inward toward the galactic center reveals a brighter, denser concentration of light. The combined glow of billions of stars in the central bulge, creating a luminous region that dominates that portion of the sky, its brightness far exceeding the outer disk's contribution. This shift in perspective reminds you that the Milky Way band visible from Earth represented your view from a position within the galactic disk, looking along its plane, the accumulation of distant disk stars, creating that characteristic band of light. From your current location deeper in the inner galaxy, you remain within the disk, but your position relative to the overall structure has changed. The outer regions now farther behind you, while the dense inner zones lie ahead. The stellar distribution around you reflects this new context. Stars visible in all directions, but concentrated most strongly within the disk plane. with noticeably fewer stars visible when looking perpendicular to that plane toward the galactic poles. You inhabit a flattened structure, your position within that structure granting you different views depending on which direction you observe. The spacecraft continues its inward trajectory through regions where stellar number density climbs steadily higher, each passing 1,000 light years, bringing you into zones where stars pack more closely together, on average, than in the regions behind. The night sky from any hypothetical planet orbiting a star in these inner regions would display thousands of stars visible to the naked eye, compared to the few thousand visible from Earth's less crowded neighborhood. The accumulated light from these numerous stars would create a persistent background glow even during the planet's night. The darkness between stars never becoming as complete as the darkness familiar from Earth's rural locations. The sheer number of nearby suns contributing enough light to maintain perpetual twilight conditions. Such an environment would profoundly affect any life that evolved there. The concept of true darkness, foreign to organisms accustomed to star-filled skies that never dim completely. The stellar velocities you measure show the gravitational influence of the galaxy's central mass concentration, becoming stronger with decreasing distance from the core. The orbital speeds of stars increasing to counterbalance the enhanced gravitational pull from the billions of suns located in the central bulge ahead. Stars here orbit the galactic center at speeds exceeding those typical in the solar neighborhood. Their faster motion, reflecting the need to maintain stable orbits when circling through regions where the enclosed mass, all the matter residing within their orbital radius, reaches higher values than in the outer galaxy. This relationship between orbital radius and velocity reveals information about how mass distributes itself throughout the galaxy. The rotation curve describing how orbital speed changes with distance, from the center providing evidence for structures visible and invisible alike. Temperature variations become apparent in the ambient radiation field pervading this region. The combined starlight from numerous nearby stars creating a slightly warmer background environment than exists in the outer galaxy's more sparsely populated zones. While interstellar space everywhere maintains temperatures far below anything considered warm by human standards, the relative increase here reflects the enhanced radiation density. Photons from thousands of stars passing through each region of space, creating a measurable energy flux. Dust grains that exist in the remaining interstellar medium absorb this radiation and reach equilibrium temperatures slightly higher than equivalent grains in the outer galaxy. Their thermal emission contributing to the infrared background that suffuses the inner regions. These temperature differences remain subtle, measured in tens of degrees on the Kelvin scale, but they represent real physical consequences of inhabiting a denser stellar environment. You observe stellar types that appear less commonly in the outer galaxy, stars whose formation or evolution depends on the conditions prevalent in these inner zones. Closed binary systems where two stars orbit mere stellar radii apart occur more frequently here. The higher stellar density during formation epochs making gravitational capture and close encounters more probable when young stars first condensed from their parent clouds. Some of these binaries exchange mass through gravitational interaction. Material from one star flowing towards its companion through an accretion disk, the process generating X-rays detectable even across the thousands of light years separating your spacecraft from the interacting pair. Other systems contain white dwarfs or neutron stars, the compact remnants of massive stars that died in supernova explosions. Their presence enriching the environment with heavy elements forged during stellar collapse. The sense of approaching something massive strengthens as your journey continues. The gravitational architecture of the inner galaxy, reflecting the presence of the central bulge and the supermassive black hole residing at its heart. Stars here orbit under the influence of the billions of solar masses concentrated in the galactic center region, their motions choreographed by gravity into patterns that maintain the overall structure's stability. The bulge ahead contains some of the galaxy's oldest stars, a population that formed when the Milky Way first assembled and has remained gravitationally bound to the central regions throughout the galaxy's history. This ancient stellar population represents a fossil record of conditions present during galaxy formation, each star preserving in its chemical composition clues about the environment that existed when it formed more than 12 billion years ago. The view back towards the outer galaxy reveals the distance you have traversed, the Sun and Earth too far away and too faint to detect individually among the countless stars scattered across that direction. Your origin point now lies lost among millions of similar yellow dwarf stars, the solar neighborhood undistinguished at this range, its distinctiveness to you a matter of perspective rather than any objective characteristic, making it special compared to other star systems. This realization creates a strange mixture of scale and significance. The recognition that home represents just one system among billions, combined with the awareness that your personal reference frame makes it central to your experience regardless of its cosmic ordinariness. The galaxy contains multitudes, each star potentially accompanied by planets, some perhaps bearing their own observers looking outward and contemplating their position within this immense structure. Ahead, the galactic bulge looms larger and brighter, its concentration of billions of stars creating a region of enhanced stellar density that represents the transition from the disk's structured spiral arms to the ancient elliptical distribution of the central stellar population. The bulge represents a different type of structure than the disk, its stars orbiting in randomly oriented elliptical paths, rather than the disk's orderly circular motion. The velocity distribution, isotropic rather than aligned with galactic rotation. This component of the galaxy hosts its own distinct stellar population and dynamical characteristics, a sphere of old stars surrounding the very center where the supermassive black hole waits. Your trajectory aims toward that heart, the journey's ultimate destination, residing within the bulge's innermost regions, where stellar density reaches its maximum and gravitational forces peak. The spacecraft presses forward through these increasingly populated regions, each parsec bringing you deeper into the galaxy's inner zones, where density and brightness climb toward the extreme values characteristic of the central regions themselves. The journey continues its slow progression through space and time, measured in light years of distance and years of subjective passage, carrying you ever closer to the galactic center, where the final stages of this voyage await. The spacecraft enters the galactic bulge proper, crossing from the disk's structured spiral organization into the ancient spherical concentration of stars that surrounds the Milky Way's heart. And the stellar environment transforms into something fundamentally different from any region you traversed previously during this long journey. The stars here packed together far more tightly than in the disk regions behind you. Their number density reaching levels where the average separation between neighboring suns measures in light weeks or light months rather than the light years typical of the solar neighborhood. You find yourself traveling through a stellar crowd rather than the sparse distribution familiar from Earth's galactic location. Stars visible in every direction, at distances close enough that their individual colors and characteristics stand out clearly against the background glow. The bulge contains approximately 20 billion stars in a roughly spherical volume. Its stellar density in the innermost regions exceeding that of the disk by factors of thousands, creating an environment where gravitational interactions and stellar encounters occur far more frequently than in the galaxy's outer zones. The view from this region would appear spectacular from any planet orbiting a bulge star, the night sky displaying not the few thousand stars visible to the naked eye from Earth, but tens of thousands of stars, bright enough to distinguish individually, their combined light creating illumination levels during the planet's night period comparable to twilight conditions on Earth. The accumulated starlight from so many nearby suns would allow someone standing on such a planet's surface to see clearly, without artificial light, even during hours when the local star remained below the horizon, the stellar background providing enough illumination to cast faint shadows and illuminate landscapes in soft multicolored glow. True darkness would never occur on such a world. The night sky so crowded with bright stars that the spaces between them would appear filled with fainter stellar points, extending down to the limits of unaided vision. This environment would profoundly shape any civilization arising there, their astronomy developing without the darkness humans experienced from Earth. Their relationship with the cosmos necessarily different when surrounded by such obvious stellar abundance. The stellar population here differs markedly from the disk's mixed-age community. The bulge stars, representing predominantly old generations, formed during the galaxy's earliest epochs, more than 10 billion years ago. These ancient suns, condensed from gas clouds, enriched by the first stellar generations. Massive stars that formed when the universe itself was young and lived fast before exploding in supernovae that scattered heavy elements into their surroundings. The bulge stars you observe now carry that chemical heritage, their spectra showing absorption lines from iron and other metals, produced during those primordial stellar deaths and incorporated into subsequent star-forming clouds. This population contains few young blue stars, the bulge's gas having been largely converted to stars billions of years ago, leaving insufficient raw material to sustain the ongoing star formation that characterizes the disk's spiral arms. Red giants appear frequently throughout this stellar crowd, evolved stars that exhausted the hydrogen fuel in their cores and expanded to enormous sizes, their surfaces cooling while their overall luminosity increased dramatically. You pass within light months of several such giants, their orange and red disks visibly larger than typical main sequence stars, their diffuse outer atmospheres extending across volumes that could contain the inner solar system's planetary orbits. These stars shed material continuously through stellar winds, gas flowing outward from their extended atmospheres into the surrounding interstellar medium at speeds of tens of kilometers per second. The expelled material carries heavy elements forged inside the star through nuclear fusion. Carbon and nitrogen and oxygen produced during the star's long main sequence lifetime and during the helium burning that powers its current giant phase. This enriched gas eventually mixing with the interstellar medium to become available for incorporation into future stellar generations. The interstellar medium itself exists in diminished form here. Compared to the disk regions, most of the bulge's original gas having been converted into stars long ago during the intense star formation that occurred when the galaxy first assembled. What gas remains exists primarily as material returned to space by dying stars. The stellar winds from red giants and the ejected envelopes of planetary nebulae, adding small amounts back to the interstellar reservoir, but insufficient to fuel significant new star formation. The environment feels depleted of raw material, the star-forming process having run largely to completion in this region, leaving a population of aging stars slowly evolving through their final stages. Dust appears rarely, present only in small amounts around certain evolved stars, where it condenses from material in their stellar winds, the grains forming when temperatures drop sufficiently for atoms to combine into solid particles that drift outward into space. You notice the stellar motions here differ from the orderly rotation characteristic of disk stars. The bulge population moving in randomly oriented elliptical orbits rather than circular paths aligned with the galactic plane. Individual stars travel in all directions, some moving inward toward the galactic center, while others travel outward toward the bulge's edge, their velocities reflecting the complex gravitational environment where the collective pull from billions of neighbors determines each star's trajectory. This velocity distribution creates what astronomers call a pressure-supported system, where random stellar motions counterbalance gravity rather than the organized rotation that supports the disk against gravitational collapse. The bulge resembles a miniature elliptical galaxy embedded within the Milky Way's disk, its dynamical properties reflecting its formation through different processes than the disk's gradual assembly from rotating gas clouds. The spacecraft's passage through this crowded environment requires awareness of the increased stellar density, though even here the distances between stars remain vast by human standards. Each sun, still separated from its neighbors by trillions of kilometers of mostly empty space. The probability of close stellar approaches remains extremely low, despite the enhanced density. The galaxy's stars so small relative to the distances separating them that collisions or near misses occur rarely even in the bulge's densest regions. You pass within a few light weeks of numerous stars during your traverse, close enough to observe their characteristics in detail, but never approaching near enough for their gravitational influence to significantly affect the spacecraft's trajectory. Each passage offers views of different stellar types, some resembling the Sun in size and color, others swollen into giant configurations, a few appearing as small hot white dwarfs that represent the exposed cores of former giant stars whose outer layers drifted away thousands of years ago. Temperature measurements show the stellar radiation density here far exceeding levels found in the outer galaxy. The combined light from thousands of nearby stars, creating an intense photon field that bathes everything in this region. While interstellar space maintains temperatures far below freezing everywhere in the galaxy, the enhanced radiation here raises the ambient temperature of the interstellar medium by measurable amounts compared to regions farther from the galactic center. Dust grains that exist in the sparse interstellar medium absorb starlight and reach equilibrium temperatures determined by the balance between absorbed radiation and emitted thermal infrared. These temperatures running higher in the bulge than in the disk's outer regions. The effect remains small in absolute terms, differences of tens of degrees on scales where temperatures measure in the hundreds of Kelvin. But the variation represents real physical consequences of inhabiting different locations within the galaxy's structure. The gravitational environment strengthens noticeably as your journey carries you deeper into the bulge's inner regions. The spacecraft traveling under the influence of the enormous mass concentration residing in the galactic center ahead. The billions of stars comprising the bulge create a collective gravitational field that shapes the motion of everything in this region. Stellar orbits responding to the combined pull from all surrounding matter rather than any single dominant body. Your trajectory curves through this field, following a path that carries you inward toward the very center where the galaxy's supermassive black hole resides. Its 4 million solar masses, representing only a small fraction of the bulge's total mass, but concentrated into a region so compact that its local gravitational influence dominates everything nearby. You observe stellar phenomena that occur more commonly in this dense environment than in the galaxy's outer reaches, systems whose formation or evolution benefited from the high stellar densities present here. Blue straggler stars appear occasionally, objects that appear younger and bluer than their neighbors, despite belonging to the same ancient population. Their characteristics explained by stellar mergers or mass transfer in close binary systems that effectively rejuvenated older stars. X-ray sources mark locations where compact objects, neutron stars, or black holes left behind by supernova explosions accrete material from companion stars, the infalling matter heating to millions of degrees before striking the compact object's surface or crossing its event horizon. Planetary nebulae glow faintly in the distance, expanding shells of gas expelled by dying stars and illuminated by the hot white dwarf cores left behind. These objects representing stars in the brief transition between their red giant phase and their final state as cooling stellar remnants. The sense of antiquity pervades this region, nearly every star you observe having formed when the universe itself was less than a quarter of its current age. Their existence spanning most of cosmic history since the first galaxies assembled. These stars witnessed the Milky Way's evolution from a chaotic collection of gas clouds and proto-galactic fragments into the organized spiral structure it displays today. They survived billions of years while the disk formed around them, while spiral arms emerged from density waves, while the sun condensed from an interstellar cloud and Earth formed from the debris surrounding it. The bulge stars represent ancient cosmic citizens, their long lives granting them perspective on timescales that dwarf human history. Their chemical compositions preserving records of conditions present when the galaxy was young and the universe contained fewer heavy elements than it does today. The view outward, toward the galaxy's edge, grows increasingly obscured by intervening stars and the remaining dust scattered through this region. The sheer number of stellar points blocking clear sightlines toward the disk's outer zones. Looking back in the direction you came reveals layers upon layers of stars at different distances. Foreground objects blocking background ones in a complex three-dimensional arrangement that makes it difficult to perceive the spiral structure you traversed earlier. The Milky Way band, visible from Earth, emerged from your view along the disk plane through regions with moderate stellar density. But from here, deep within the bulge, the overwhelming foreground stellar population dominates the view in all directions. The outer galaxy reduced to a general glow rather than a structured pattern. Only above and below the disk plane, toward the galactic poles, does the view open up to reveal distant extragalactic space, where other galaxies shine as faint smudges against the darkness. The spacecraft continues inward through the bulge's densely populated zones, passing through stellar environments where the sky never dims completely, where planets would bask in the combined light from thousands of neighboring suns, where the galaxy's mass concentration becomes palpable through its gravitational effects on stellar motion. The stars around you orbit the galactic center at speeds reflecting the immense mass enclosed within their orbital radii, their velocities reaching hundreds of kilometers per second as they circle the galaxy's heart. You become part of this orbital choreography, your own trajectory carrying you through the gravitational field created by billions of suns. The spacecraft following paths determined by the mass distribution throughout the inner galaxy. Temperature and radiation levels continue their gradual increase as you approach ever closer to the galactic center. Each reduction in distance bringing you into regions where stellar density climbs higher, and the combined output from nearby stars grows more intense. The environment remains safe for passage, radiation levels well below anything that would threaten properly shielded instruments. But the trend toward higher density and intensity continues steadily as your destination approaches. The innermost regions of the bulge blend into the nuclear star cluster, an extremely dense concentration of stars residing within the central few parsecs. The stellar environment there representing the most crowded region in the entire galaxy. Ahead, the galactic center itself waits, marked by radio emission from the supermassive black hole called Sagittarius A star, by the orbital motions of stars moving at percentages of light speed around the central mass, by the extreme environment where stellar density reaches its peak, and where gravity warps space itself. Your journey approaches its ultimate destination, the spacecraft pressing forward through the bulge's innermost zones, toward the heart of the Milky Way, where the final stages of this voyage will unfold. The distance remaining measures now in parsecs rather than thousands of light years. The cosmic address narrowing toward the single point around which 400 billion stars orbit, the anchor of our island universe, the center toward which you have traveled across the galaxy's full radius. The spacecraft approaches the innermost regions of the galactic center, entering the zone astronomers call the central parsec, a sphere approximately 3 light-years in diameter surrounding the supermassive black hole at the Milky Way's heart. And you find yourself in the most extreme stellar environment the galaxy contains. The stellar density here exceeds anything you encountered during the long journey from Earth. Stars packed so tightly together that millions of suns occupy a volume that, in the outer galaxy, might contain only a handful of stellar systems. You observe stars separated from their nearest neighbors by distances measured in light weeks or even light days. The average spacing between suns shrunk to levels where close gravitational encounters become common rather than rare, where stellar motions reflect not just the collective pull from the galaxy's total mass, but also perturbations from frequent near passes by neighboring stars. The S-stars dominate your attention, a cluster of young hot stars orbiting very close to the galactic center, on highly elliptical paths that carry them from relatively distant positions down to within light hours of the central black hole, before they swing outward again. These stars appear as brilliant blue-white points, moving noticeably fast against the background stellar population, their orbital velocities reaching percentages of light speed during closest approach to the center. Their motion visible even across the time it takes you to observe them. Star S2, also designated SO2, follows one of the best-studied orbits, completing a full circuit around the galactic center every 16 years with an elliptical path that brings it to within about 17 light hours of the black hole at periapsis, the point of closest approach before carrying it back out to distances of several light days at apoapsis. Watching these stars move reveals the presence of the supermassive black hole through pure gravitational influence. Their extreme velocities and tight orbits, requiring an enormous mass concentration, occupying a very small volume at the center. Careful measurements of S2 and its companions over decades of observation from Earth allowed astronomers to determine that approximately 4 million solar masses must reside within a region smaller than the orbit of Uranus, the only object capable of fitting such mass into such a compact space, being a black hole, from which not even light can escape. The S-stars themselves present a puzzle regarding their formation. Young hot stars existing in an environment where the tidal forces from the central black hole should have prevented normal star formation, their presence suggesting they formed elsewhere and migrated inward, or condensed from processes astronomers continue working to understand. You observe the central cluster more broadly. Thousands of stars orbiting within the inner parsec, in paths that carry them around the galactic center at velocities far exceeding typical stellar motions elsewhere in the galaxy. The cluster contains old stars, inherited from the ancient bulge population, alongside the younger S-stars, a mixture of ages and types, all bound by the overwhelming gravitational influence of the central mass. These stars experience an environment profoundly different from conditions in the solar neighborhood, their paths carrying them through regions where they pass near countless other stars, where radiation from nearby neighbors creates a background vastly more intense than the sparse stellar environment surrounding the Sun, where gravitational perturbations from close encounters could potentially disrupt planetary systems if such systems manage to form and survive in this hostile zone. The view here would appear extraordinary from any vantage point, the night sky crowded so densely with stars that individual points of light blend together in the innermost regions, creating a continuous glow rather than distinct stellar positions. Thousands of stars would appear bright enough to cast shadows, their combined light creating illumination levels during night hours exceeding those of the full moon, as seen from Earth by factors of thousands or more. The galactic center's stellar density creates an environment where true darkness never falls, where the accumulated light from millions of nearby suns maintains perpetual daylight-level illumination, regardless of any local star's position below a planet's horizon. Such an environment seems fundamentally incompatible with the existence of planets suitable for life. As Earth knows it, the radiation levels and gravitational perturbations making stable clement conditions nearly impossible to maintain over the billions of years required for biological evolution. The spacecraft's instruments detect intense radiation across multiple wavelengths. The galactic center glowing not just in visible light, but in infrared, X-rays, and radio emissions that reveal different aspects of the extreme environment. Infrared observations penetrate the dust that obscures visible light views of the innermost regions, revealing the stellar population and warm dust clouds surrounding the center. X-ray emission emerges from hot gas heated to millions of degrees by supernova explosions and stellar winds, from accretion onto compact objects, where infalling material converts gravitational potential energy into thermal radiation before disappearing into neutron stars or black holes. And from the immediate environment around Sagittarius A star itself, where matter approaching the supermassive black hole heats to extreme temperatures. Radio emission marks the location of the black hole with remarkable precision. Synchrotron radiation from relativistic particles spiraling in magnetic fields, creating a compact radio source that pinpoints the galactic center's exact position. You observe gas and dust clouds threading through the central parsec, material heated by the intense stellar radiation field to temperatures that cause it to glow in infrared wavelengths detectable from instruments aboard your spacecraft. Some clouds appear as dark silhouettes against the background stellar glow, dense enough to block light from stars behind them, despite the overwhelming brightness of this region. Other clouds emit their own light, heated by radiation from nearby stars or shocked by stellar winds and supernova blast waves that plow through the interstellar medium. One particularly notable cloud, designated G2, passed very close to the galactic center during 2014. Its close approach allowing astronomers to study its interaction with the environment near the supermassive black hole and test predictions about how the black hole would respond to this temporary increase in available material. The tidal forces in this region grow increasingly powerful as you approach the very center, gravitational gradients becoming steep enough to stretch objects along radial lines, while compressing them perpendicular to that direction. These tidal effects arise because gravity strengthens with proximity to a massive object, the near side of any extended body experiencing stronger pull than the far side, creating forces that attempt to elongate the object along the direction pointing toward the mass concentration. For small objects like spacecraft, the effect remains negligible, even very close to the black hole. But larger objects like gas clouds or stars begin experiencing significant tidal stress as they approach within the innermost regions. The eventual limit of this process defines the tidal disruption radius, the distance within which tidal forces from the black hole overcome an object's self-gravity and tear it apart, different for objects of different sizes and densities. The orbital dynamics here reveal information about the black hole's properties beyond just its mass. The precise motions of stars like S2 during their closest approaches, allowing tests of general relativity in the strong gravitational field regime. Observations of S2's periapsis passage in 2018 detected gravitational redshift, the lengthening of wavelengths as photons climb out of the deep gravitational well surrounding the black hole, exactly as predicted by Einstein's theory. The star's orbit also showed evidence of relativistic precession, the ellipse itself slowly rotating over time due to the warping of space by the central mass. Another general relativistic effect that differs from the predictions of Newtonian gravity. These observations confirmed that general relativity accurately describes gravitational phenomena, even in the extreme environment near a supermassive black hole. The theory passing tests conducted under conditions impossible to replicate anywhere in the solar system. You observe the region called the circumnuclear disk, a structure of gas and dust orbiting the galactic center at distances of roughly 1 to 7 parsecs, outside the central cavity where the S-stars reside, but still deep within the gravitational influence of the supermassive black hole. This disk contains molecular clouds, dense regions where hydrogen exists primarily in molecular form rather than as individual atoms. Their higher density, making them sites where star formation could potentially occur despite the challenging environment. The disk rotates around the galactic center, with velocities reaching hundreds of kilometers per second, its motion reflecting the enormous enclosed mass, pulling it gravitationally, while its angular momentum prevents it from falling directly inward. The sense of approaching something fundamentally different from all previous stellar objects becomes palpable as you near the very center, the realization settling in that ahead lies not another star or gas cloud, but a region from which nothing, not even light itself, can escape once it crosses a critical boundary. The supermassive black hole Sagittarius A star represents mass compressed into such a small volume that it curves space around itself so severely that escape becomes impossible within a certain radius. The event horizon marking that point of no return. Everything you have observed during the journey, all the stars and gas clouds and stellar remnants, consisted of matter you could in principle approach and then leave. Objects whose gravity could be overcome by sufficient velocity or propulsion. But a black hole permits no escape from within its event horizon. Any trajectory that crosses that boundary leads inexorably inward. All possible futures for matter and light alike, pointing toward the central singularity. The spacecraft slows its inward progress, maintaining a safe distance from the innermost regions where the gravitational field becomes strong enough to require significant energy to resist. You observe the central zone from a distance, measured in light weeks, close enough to study the environment in detail, but far enough to avoid the extreme tidal forces and radiation levels characteristic of the immediate vicinity of the black hole. From this position, you can observe the orbital motion of the S-stars, watch gas clouds as they navigate the central region, and measure the radiation emerging from the accretion processes occurring around Sagittarius A star. The view shows a stellar environment pushed to its limits, stars crowded together more tightly than anywhere else in the galaxy, orbiting at velocities that reflect the immense mass concentration whose pull governs everything here. The journey from Earth to this point has traversed the galaxy's full radius, carrying you across 26,000 light-years from the familiar solar neighborhood through the spiral arms and interstellar voids, past stars of every type and age, through the transition into the ancient bulge population, and finally to the dense stellar environment surrounding the galactic center. You have moved from a quiet region where stars space themselves light-years apart to this crowded inner zone where stellar separations shrink to light weeks. From a young stellar population, rich in heavy elements, to ancient stars formed when the universe contained far less processed material. From a location where the galaxy's center appeared as a distant radio source, to this position where its presence dominates the gravitational environment and determines every orbital trajectory. The supermassive black hole ahead represents the journey's final destination, the anchor point around which the entire galaxy orbits, the mass concentration that holds the Milky Way together through gravitational attraction. 400 billion stars follow paths determined ultimately by this central object, their orbits organized into the disk and bulge and halo structures that define our galaxy's shape. The black hole itself, despite its 4 million solar masses, making it enormously massive by stellar standards, comprises only a tiny fraction of the galaxy's total mass. Yet its central position makes it the point around which everything else moves, the reference frame from which galactic rotation measures itself, the heart toward which you have journeyed across the breadth of our island universe. The spacecraft prepares for the final approach toward the galactic center itself. Instruments locked onto the radio emission from Sagittarius A star. Trajectory calculated to bring you as close as safely possible to observe the supermassive black hole and its immediate environment. Ahead lies the conclusion of this journey, the arrival at the center, the encounter with one of the universe's most extreme objects, the destination awaited across 26,000 light-years and uncounted years of travel, at speeds exceeding light itself. The spacecraft takes its final position in the innermost stable region surrounding Sagittarius A star, the supermassive black hole at the galactic center, and you find yourself observing one of the universe's most extreme objects from a distance measured in light days, close enough to study its environment in detail, while remaining outside the zones where tidal forces and radiation reach destructive intensities. The black hole itself remains invisible in the conventional sense, its defining characteristic being that it prevents light from escaping once that light crosses the event horizon boundary. But its presence announces itself through gravitational effects on everything nearby and through the radiation emitted by material falling toward it. You observe a region where space curves so severely under the influence of concentrated mass that the normal rules governing motion and light propagation bend into configurations impossible anywhere else in the galaxy. The event horizon, the boundary defining the black hole's point of no return, resides approximately 12 million kilometers from the central singularity, a sphere whose radius corresponds to what astronomers call the Schwarzschild radius for a non-rotating black hole of 4 million solar masses. This radius represents the distance at which escape velocity equals the speed of light, meaning any object closer than this distance would need to move faster than light to escape the gravitational pull, an impossibility according to the laws of physics as currently understood. The event horizon marks not a physical surface, but a mathematical boundary in space-time, a one-way membrane that permits matter and energy to cross inward, but forbids anything from crossing outward. Information and particles and light alike becoming permanently trapped once they enter this region. From your external vantage point, you can never observe what happens inside the event horizon, those regions remaining forever hidden behind the boundary that defines the black hole's edge. The size of this boundary, while enormous by human standards, appears remarkably small given the immense mass it contains. The 4 million solar masses, compressed into a sphere that would fit comfortably within Mercury's orbit around the Sun. This compactness defines black holes, objects where mass concentrates so extremely that they collapse gravitationally into configurations from which escape becomes impossible. Their density, approaching infinity at the central singularity, according to general relativity's predictions. The black hole you observe, formed through processes still debated among astronomers, possibly from the direct collapse of massive gas clouds during the galaxy's early history, possibly through the gradual merger of smaller black holes that sank toward the galactic center through dynamical friction, likely through some combination of growth mechanisms that accumulated mass over billions of years of galactic evolution. You observe the region surrounding the event horizon, where space warps dramatically under the black hole's gravitational influence, light following curved paths as it propagates through the distorted space-time geometry. This gravitational lensing creates visual effects impossible to see anywhere else. Background stars appearing in distorted positions as their light bends around the black hole on its way toward your spacecraft. The massive object acting like an enormous gravitational lens that redirects photons along curved trajectories. Stars almost directly behind the black hole, from your perspective, appear spread into ring-like configurations called Einstein rings. Their light bent around both sides of the black hole before reaching you. The symmetry of the alignment creating a complete circle of light surrounding the dark region where the event horizon resides. Less perfect alignments produce arcs and multiple images, individual stars generating several distinct apparent positions as their light takes different curved paths through the warped space around the black hole. The accretion disk surrounding Sagittarius A star appears as a faint glow of material spiraling inward toward the event horizon. Gas and dust captured by the black hole's gravity and gradually falling inward while conservation of angular momentum forces it into a rotating disk structure. The material in this disk originates from stellar winds shed by nearby stars, from gas clouds that ventured too close to the central region, from the slow accumulation of diffuse interstellar medium over millions of years. As this material spirals inward, it gradually moves faster to conserve angular momentum. Particles in inner regions orbiting more rapidly than those farther out. This differential rotation creating friction between adjacent layers of the disk. The friction heats the gas to temperatures reaching millions of degrees in the innermost regions, the thermal energy causing it to emit radiation across the electromagnetic spectrum before it crosses the event horizon and disappears from view. The disk appears relatively dim compared to accretion disks around supermassive black holes in more active galaxies. Sagittarius A star, consuming material at rates far below what the black hole could potentially accept. The accretion proceeding in what astronomers call a low luminosity mode. This subdued feeding results from the sparse material density in the galactic center environment, the gas available to accrete, existing in insufficient quantities to fuel the brilliant quasar-like emission that characterizes actively feeding supermassive black holes in younger or more gas-rich galaxies. The Milky Way's center went through more active phases earlier in the galaxy's history, when gas densities ran higher and the black hole accreted more vigorously. But today's relative quiescence creates a black hole that reveals itself through subtle radiation and through gravitational effects, rather than through overwhelming luminosity. The innermost stable circular orbit defines the closest distance at which material can orbit the black hole indefinitely without falling inward, located about 3 times the event horizon radius for a non-rotating black hole and closer for rotating ones. Material orbiting inside this radius experiences no stable circular paths. All orbits at smaller radii being unstable and leading inevitably to plunge across the event horizon within a few orbital periods. You observe gas in the accretion disk, reaching this innermost stable region, orbiting rapidly for a brief time before the final plunge inward. The material there moving at significant fractions of light speed as it whips around the black hole in its final moments of visibility. The transition from stable orbit to final plunge happens rapidly once material crosses the innermost stable orbit, the gas spiraling inward across the event horizon and vanishing from the observable universe. Time dilation effects become significant in the strong gravitational field near the event horizon, clocks running more slowly when deep in the gravitational well compared to clocks at larger distances or in weaker fields. Light emitted from material close to the event horizon appears redshifted when observed from your safer distance, the photons losing energy as they climb out of the gravitational potential well, their wavelengths stretching toward the red end of the spectrum. This gravitational redshift increases for material closer to the black hole. Light from gas approaching the event horizon becoming increasingly redshifted until, at the boundary itself, the redshift becomes infinite and the light loses all its energy trying to escape, effectively rendering the event horizon invisible to external observers. From the perspective of someone watching material fall into a black hole, the infalling matter appears to slow down as it approaches the event horizon, its image becoming dimmer and redder, asymptotically approaching but never quite reaching the boundary in the external observer's timeframe. Even though the infalling matter experiences crossing the horizon in finite time on its own clocks. You observe magnetic fields threading through the accretion disk and the region surrounding the black hole, field lines anchored in the inflowing material and twisted by the disk's differential rotation. These magnetic fields play important roles in the accretion process, transporting angular momentum outward through the disk and allowing material to lose enough rotational energy to fall inward. Without this angular momentum transport mechanism, the gas would remain in orbit rather than accreting onto the black hole. The fields also channel some fraction of the infalling material into jets, narrow beams of particles and radiation launched perpendicular to the disk plane at velocities approaching light speed. Though Sagittarius A**'s jets appear weak compared to the powerful relativistic jets emerging from more actively accreting supermassive black holes in other galaxies. The immediate environment around the black hole emits X-rays and radio waves detectable by your spacecraft's instruments. The X-rays, emerging from gas, heated to tens of millions of degrees by accretion processes and by shocks in the turbulent flow near the black hole. Radio emission comes from synchrotron radiation, high-energy electrons spiraling in magnetic fields and emitting photons in the process. The compact radio source, called Sagittarius A**, marking the black hole's position with remarkable precision. The radio emission varies on timescales of hours to days, flickering and flaring as conditions in the innermost accretion region change. Turbulence in the flow, creating temporary bright spots that shine briefly before dissipating. These variations allow astronomers to probe the size of the emission region, the rapid changes indicating that the radio-emitting zone must be compact. Light travel time arguments, limiting its size to roughly the distance light can travel during the duration of a flare. Looking outward from this central position reveals the galaxy spreading away in all directions. The spiral disk extending across hundreds of thousands of light years, while the bulge surrounds you with its ancient stellar population. The journey that brought you here traversed that entire structure, carrying you from Earth's location in a minor spiral arm through the disk's full radial extent to arrive at this central point. 400 billion stars orbit around this location. Their paths determined ultimately by the combined gravitational pull from all the galaxy's mass, with the central black hole representing just one component, albeit the component occupying the mathematical center of the galaxy's rotation. The Milky Way stretches across space as an organized structure because gravity and rotation balance each other. The galaxy's matter, moving fast enough to avoid collapsing inward, but not so fast as to fly apart. The equilibrium maintained for billions of years, producing the stable configuration visible today. The black hole represents an end state of gravitational collapse. Matter compressed so severely that no known physical force can halt its contraction. The final singularity predicted by general relativity, representing a point where density becomes infinite and space-time curvature reaches extremes that break down the classical theory itself. Quantum effects likely become important at these scales, the singularity perhaps replaced by some quantum gravitational structure that current physics cannot describe, the very interior of the black hole remaining uncertain territory, where general relativity and quantum mechanics both claim jurisdiction, but neither provides complete answers. These questions remain theoretical for external observers, the event horizon hiding the central regions and preventing any information about the singularity's nature from reaching the outside universe. The journey from Earth to this point has fulfilled its intended purpose, carrying you across the galactic radius to observe the Milky Way's heart, the supermassive black hole around which our entire stellar system orbits. You have traveled through the full diversity of the galaxy's structure, encountering spiral arms and interstellar voids, passing stars young and old, transiting from the disk's organized rotation to the bulge's random orbits, witnessing environments from sparse to crowded as stellar density increased toward this central region. The voyage has revealed the galaxy as a complex three-dimensional structure containing hundreds of billions of stars, organized by gravity and rotation into patterns that persist across cosmic timescales. The Milky Way representing just one island universe among billions scattered through the observable cosmos. The spacecraft maintains its position near the galactic center, instruments recording data about the black hole's properties and its surrounding environment. Observations contributing to humanity's understanding of these extreme objects that anchor galaxies across the universe. Sagittarius A star shares characteristics with supermassive black holes detected at the centers of most large galaxies, these objects appearing as a standard feature of galactic architecture rather than rare exceptions. Their formation and growth intimately connected to the evolution of their host galaxies over cosmic history. The black hole and the galaxy grew together, influencing each other through processes still being worked out by astronomers. The energy released by matter accreting onto the black hole, potentially regulating star formation in the surrounding galaxy, while the galaxy's gas supply determines how rapidly the black hole can grow. The view here contains wonders enough to satisfy curiosity about the galaxy's heart, the environment revealing itself as both more extreme than the familiar solar neighborhood and yet governed by the same physical laws that operate everywhere. Gravity and thermodynamics and electromagnetism working together to produce the structures and phenomena observable around the supermassive black hole. The journey has demonstrated that the universe remains comprehensible even in its most extreme environments, that human understanding can extend from the comfort of Earth across light years and parsecs to encompass phenomena as exotic as black holes and as vast as galactic structure. That observation and reason together allow exploration of realms far beyond physical reach. The spacecraft could linger here, studying the galactic center's environment. Or it could begin the long return journey toward Earth, crossing back through the bulge and disk to arrive eventually at the solar neighborhood where this voyage began. The universe offers destinations beyond number, each star potentially accompanied by planets, each galaxy containing billions of stellar systems, the cosmos revealing new wonders whenever curiosity directs attention toward previously unexplored regions. The journey to the galactic center represents one voyage among countless possibilities, one path through the three-dimensional landscape of stars and gas and dark matter that comprises our galaxy. One exploration of the structures accessible to those willing to travel vast distances and observe carefully what exists. The Milky Way continues its slow rotation around the central black hole, stars following their orbits as they have for billions of years. The galactic structure persisting through timescales that dwarf human history. And you rest here at the heart of that structure, having journeyed from the familiar Earth through the diversity of galactic environments to arrive at this central point, the destination awaited across 26,000 light-years, and the final part of this long voyage through the island universe we call home.